Welcome everybody to Graduate Algorithms Office Hours. We will be doing exam 1 prep today. So the exam is coming up for everybody. It's this Thursday. What I plan to do today is sort of go over some tips, cover some of the material really quickly because we've already had 2 office hours dedicated to each topic. I will point out in certain points like, oh yeah, go back to watch the previous office hours if you haven't. I'm going to go over a ton of problems today, mostly the ones that were given to you as practice problems. I will try to finish them all today. If I don't, I may consider running a second follow-up office hours later this week. I'm not sure yet. See how quickly we can get through all these. Okay. So as always, this will be recorded and it will be shared with the rest of the class. So if you decide to chat or speak up, ask questions, you will be part of the recording. So just be aware of that. So the exam 1 layout, make sure you read the post on ed. I think it should be posted on Monday. If it hasn't already, it'll be posted Monday. That'll go over all the details of the exam and what you need to be aware of and how you should approach it. But in general, here's the very, very basic summary of it. There will be 1 divide and conquer design question, and there will be 2 dynamic programming design questions. These are going to be very similar to your homework. So you should know what that format and what that what the question will be similar to. It won't be exactly the same, but it will be of the same difficulty as your homework problems. And then there will be a set of multiple choice questions related to all the topics that you've covered up to this point. And so each of these sections, so the divide and conquer is worth 20 points. The dynamic programming part is worth 10 points each, so that's also 20 points. And the rest of the multiple choice questions will be also 20 points. Dr. Bradle said that the homework is intended to be more difficult than the exam questions. I think that's fair to say. So I think mostly the reasoning behind that is you see the homework, you see the practice problems, and you are likely to see a similar problem or a problem, that you have experience with on the exam. And so it should feel easier, honestly. Whether it's actually easier or not, it kind of depends person to person. Someone might read the homework problem and immediately understand it. Someone might read the exam problem and immediately understand it. So yeah, so go with that. So dynamic programming solutions, they are, they have different parts. So you have your subproblem definition, which is, I guess we covered this before. It's the rewording of your problem mostly with a subset of your input, and then deciding whether you need to use AFI or not. Okay, so you want to reword the problem as this is your input. Your limited input is what's in scope on your subproblem definition, and then deciding whether you include AFI or not, whether you need to make a decision at AFI or not. These are important for the solution. Okay, then you define the recurrence of the subproblems. You include the base case, include the range. Is this my correct slides? 1 second. Should be my correct slides. Let me just double check. Because I thought I put in the point valuation for this for you guys so that you can see it more clearly. But this might be an old version. 1 second. Where are my files? Unless I updated the wrong. Well, let's do it here then, since I think it's helpful to know what each point value is. It should be the same regardless of homework or the exam. So let's take it to homework. Look at how homework 1 was broken down. And you should have seen this already, but just in case. 262. Okay, so this is 2 points. This is 6 points. And this is 2 points. Okay. All right. So again, include the base case, include the range, index your inputs from one, use mathematical notation, do not reference on-set values, self-reference or set conflicting values, and then your implementation analysis. You want to state the number of subproblems, the runtime to fill in that table, how where the final return is extracted from that table, and then state the runtime to extract the return. Now, there was a student in threads that asked if these two is always the same. I'm guessing that student didn't come to office hours, but then wasn't able to hear what I said. But these two are not always the same, so you need to be careful. Okay, so the number of subproblems is going to be the floor of your overall runtime. You have to be able to fill in your subproblems. The number of your subproblems you have is the least amount of runtime you can possibly have to fill in those subproblems. But it might take more runtime to calculate what each of those values are. And so your runtime, your overall runtime could be higher than the number of subproblems. So understand that, be careful. And so that's a dynamic programming solution. Strategies, the key is to efficiently recognize what kind of problem you are trying to solve, and then use the generic template, whether it be LIS, LCS, the CMM problems, knapsack. Write out the template that that you've studied, and then fill in all the details on what the requirements of the new problem is. I go over this quite a bit in the dynamic programming office hours, so go back and look at all those slides in that office hours if you don't know this. All right, so that is dynamic programming. I'm going to read some questions and try to answer. Okay. Are we declaring that to establish the bounds of the previous subproblem, 1i being different than 1? Your bounds are set for while 1 less than equal to I less than equal to n, or 1 less than I less than n. You're using less than equal to or less than, up to you whether you need to include your n or not. So just like a for loop, you can make it explicit. We had 2 big and multiple choices. Now I saw 2 DP and 1 DNC, and then some multiple choice. I don't know where you got the idea that you would have 2 big problems, but it is not. It is one that divide and conquer 2 dynamic problems. Yeah, and someone said there was no confirmed exam detail, and it is possible for things to change between today and the exam. It's entirely up to Dr. Brittle. I'm just giving you the details that I know about. But if Dr. Brittle wakes up on Wednesday and goes, you know what, I really don't like this exam, I'm going to change one of them, we will announce, the format change if it happens, but it is still allowed. Okay, so just because I told you what the exam format should look like doesn't mean you shouldn't check just in case. There is always partial grading in this class. Yes. Seem to recall one of the office hours, it was said that we don't have to include the range of variables in the subproblem definition. But as I've been going back, yeah, so Dr. Pagoda does it on his lectures. We do not require it. A subproblem definition is defined on that subproblem, not how to calculate it, but what that subproblem means. So having a range doesn't really matter, because at T of I, we only care about what is exactly at T of I. So you don't need the range. You absolutely do need ranges on your recurrence, because you need to start and end your recurrence. Okay. Do we need to define what n and m are? N and m are either given to you or they don't exist. So we will generally give you a input array that says 1, 2, ... n. I'm going to answer 2 more because these just basically keep coming in. I have general tips on exam. Yes. Okay. Exam layout. Exam layout, you will see again. Yeah, 1 divide and conquer, 2 dynamic programming, and a set of multiple choice questions. Okay. All right. So I have 2 questions with hands up. I'll answer them and then move on. Ravi?
Hi, Joves. Can you hear me?
Yes.
Thank you, Joves. I want to ask a quick question about how to do a DP problem. When you're doing a DP problem in the exam, is it a good idea to write out some test cases so you'll have an idea of what you'll need to write for your sub-problem and recurrence? Because I'm asking this question, Jovis, because I'm working on the homework 3 right now. I thought it would help to write down some test cases so I'd have some idea.
You got to give me a chance, Ravi.
Sorry.
Okay. I'm going to answer your question, and I appreciate your questions, and I really do appreciate your enthusiasm asking questions. But because this is going to be a really long office hours, just ask questions. I don't need to know the reason why the question is being asked. So I'm going to answer your question. Yes, if you need test cases to help you write the recurrence, you absolutely should. It's helpful for a lot of students, and it's a perfectly viable approach to solving these problems. I myself try to recognize a pattern and then just try to write out what the solution I think would be and then start testing that solution. But some students find it much easier to just write a bunch of the table, what that table would look like for either a sample input or a sample input they come up with, and then use that to drive their recurrence, and that's perfectly fine. Okay.
Thank you.
Yep. Aaron.
Hey, Jovis, can you hear me?
Yes.
Sweet. If you go back to the previous slide, I noticed that there's a subscript under one of the bullets. Actually, yeah, one more. Right. So like under section A, it says reword of problem. Oh.
Sorry, what are you looking for?
So right underneath section A, if A sub I can be dropped, there's another subscript. Does that mean anything? Yeah.
Oh, this one right here? No.
Yeah. I wonder if that's like, does that have any meaning, or is it just a typo?
Nope. It was me. I used to use the A subscript I because that's how I read these things. But then I realized the subscript I was really hard to read on slides. So instead I did underscore I, and then I forgot to remove the subscript, and that's all. That's all.
Got it. Thank you.
Yep. All right, Edward.
Oh, sorry about that. Yeah, it might be out of the scope of this office hours, but I was just wondering if you could provide some insight into things like trying to make a problem fit, for example, into, let's just say, chain matrix multiplication. Sometimes my first thought is to like start with the recurrence that I know, and from there, like, is it looking into like maybe changing boundary conditions, trying to understand, like, what I found for myself is like trying to understand the problem kind of leads me into directions that don't really help because it's sometimes very abstract as to how that affects the boundary conditions. Or is it the case that like the boundary conditions, all that stuff shouldn't change? It's just like maybe the cost function and what you define as those boundary conditions, or like could anything change?
So the boundary condition can change, and it really depends on your personal solution. I have seen solutions that work with the boundaries shifted one way or the other, and it just really depends on your solution. What I normally like to do when I solve a problem is I first consider the example, and I can try to understand what the example is, if there's an example, or understand what the problem is asking. From there, I actually start with the recurrence. I find the recurrence to be the part that after the subproblem definition, because I think that's actually the easiest part. On the recurrence part, I start with just the recurrence statement. I don't start with the boundary. I don't start with the base case, because to me, those are border your edge cases. Your recurrence, if I pick a recurrence from the very middle, like if I picked a subproblem from the very middle of the recurrence, that's all that's needed, right? That's like, what am I doing right before this? What am I looking at? Once I think I have a pretty good grasp of what the actual recurrence equation is, I then use that to go, okay, if I look back far enough, what do I need my base case to be in order for this recurrence to work? At some point, that base case has to be set to something. What should that be set to? Then I set the base case. Then I go, okay, now that I have the base case, what am I ranges? What am I iterating from to? And I start to play around with it. But to me, the part that I want to get right first is the recurrence, and then I mess around with everything around it.
Got it.
I think if you start with the base case and start with the range, you end up trapping yourself into these boundaries that you then have to try to get your recurrence to work around, which I think is far more difficult than if you just start with the recurrence that works and then put the boundaries around it.
I see.
But it's up to you.
In this case, yeah, just follow up. In this case, like the trouble for me was even stating the subproblem definition in such a way that like made the recurrence easy. What I was trying to set up a recurrence, but then the hard part was figuring out like, well, what does this recurrence mean in terms of subproblem?
Yeah, so a few things. One, the simplest thing to try is to just take your problem statement and rephrase it as a smaller part of your input. That's generally what your subproblem is. Sometimes, such as the making change problem, especially the making change K problem, where that subproblem definition that's based on the actual problem statement isn't enough, and you have to kind of change it a little bit. That can be a little tricky, but I think start with the problem statement, shorten it to be your subproblem definition, and then go, am I able to actually calculate this in the recurrence? If I can't, then maybe I can track something else in my subproblem. But your subproblem is very much related to the problem statement, so starting with that, I think, is a good approach. Okay, I'm going to answer one more, and then I'm going to keep going. Georgie? Georgie, you're muted if you're talking.
Can you hear me?
Yep.
Sorry about that. Yeah, I have a quick question about subproblem definition. So if we say A1, A2 up to AI, would that be considered as a error, since like we are kind of technically assuming I is more than 2?
You should do 1 to ... I.
Okay.
You're generally not going to be expected to take on the input that's like borderline like a 0. But in general, I think a 1 size input is legal and a 2 size input is legal. So I would think that you don't want to constrain it. So you can assume that the size of the input is at least 1, and then there should just be ... I.
Okay, cool. Thank you.
All right. Moving on. So common mistakes, I went over this last time. I'm going to show it again and just point out a few of them. Oops, you want to be especially careful on where is my pen? Not handling this. When this happens, I think students miss it more often than not. So not more often, they miss it pretty often. So be careful there. Forgetting the bounds is a big one, and then from there, all the other ones are just like small percentages here and there. Getting the wrong extraction. This is the main two that you have to consider is, do I return the final value in my table, or do I return the max of all the values in my table? So you have to kind of be careful there. Yep, went over this the first office hours, so this should be pretty simple. All right, so we're going to move to divide and conquer solutions. Your algorithm is worth 12 points. You cannot use pseudocode. You want to include the base case if needed. So when does your recursion end? Explain what part of the black box you will modify if needed, and then your justification of correctness is 4 points. Why did you pick the black box? Why did you modify the black box? And why does the base case or the final step in your recursion solve the problem? Runtime analysis is 4 points. You need to calculate the recurrence. You can either use the master theorem or substitution. You can also use Christian's method if you so choose. Okay, so what Christian's method is, and I covered this last week, is basically a logic to explain what the master theorem is comparing between its A, B, and D coefficients. And so if you decide you're not very good with master theorem, you're not very good with substitution, you can just reason it out, then that's fine. Because we don't ask you to show the math on your final runtime. As long as you show the recurrence equation, explain what part each of the equation represents in your algorithm, you can just say, based on this recurrence equation, my runtime is all n log n. That's it. You don't have to show the math. And so however you come up with that, it's up to you. Pick one, be comfortable with it going into the exam. You can assert the runtime of known algorithms. You don't have to show the runtime equation for that. You can just assert that runtime, say binary search is log n, merge sort is O of n log n. But if you make any modifications to those black boxes, you must explain how that affects runtime, even if it does not. You can say my step is O of 1 and therefore does not affect my the overall runtime. It is still O of log n. Or my runtime is now, my modification is O of n, and because binary search is normally log n, it now becomes n log n, and that is my final runtime. So that's how you want to approach it. Okay. The algorithms, that you want, the approach that you want to take is you want to break your problem into several smaller parts, smaller subproblems. Each of these are generally solved independently of each other, and then they are compared in some way. So they either eliminate work, merge work, or they cancel out the work based on what the problem is asking for. This is a form of recursion. This is effective because you are reducing work through the eliminating portion of the input, which is what binary search does. You are eliminating redundant work, which is merge sort. So it removes the redundancy of trying to compare every single element to each other. You only have to compare, one pair at a time, and then you get through it. Reducing work through math, so fast integer multiplication, and then FFT. If you decide to watch those lectures, you're taking math that is going to be done again, and then you're just eliminating redundant math. Okay. Strategies for coming up with solutions for DNC. Is the input sorted? If it's not, then if it is, then binary search is probably your best bet. It's probably something you need to at least consider, even if it's not the right answer. You're given the sorted array for a reason, so consider that. Consider modifying the target if you need to modify binary search. Consider modifying the branching logic if you need to modify binary search. Is the input unsorted? So if the input's unsorted, you can't do binary search directly. Now, what you can do is sort it and then use binary search, but be careful. Not all unsorted arrays needs to be sorted, okay? So consider fast select. Fast select finds the kth smallest element without sorting the array at all, right? So that is a valid approach. And if you were to sort the array first, it would be O of n log n, whereas fast select is O of n runtime. So don't just sort it because you told you it's unsorted. Be careful. You might not need to sort it. You can consider modifying the merge logic in merge sort. That's one approach to take. You can consider modifying the partition logic to fast select. That's another approach you could possibly take. And then there's other DNC algorithms to consider, such as FFT or fast multiply for math-based ones, and tournament algorithm for eliminations. This is the one where we went over last week on majority candidate. So that is a tournament algorithm. Okay. Any tips on recognizing when we need to sort based on the problem? So in general, if you need to find, some kth element one time, you shouldn't sort. If you need to find, the kth element and then other additional elements, it depends on how many times you need to do this. So fast select is O of n, right? So doing it k times is O of kn, right? And merge sort is O of n log n. And then once you have O of n log n sorted, finding the kth element in a sorted array is O of 1, right? So then it becomes O of k. So then it's O of k plus O of n log n versus O of k times n. So what you know about the size of n and the size of k can help you kind of decide which one is better. So if you have to do something to an array over and over again, you start to consider, oh, I should sort it first and then do this. If you just have to do something to the array one time, you may not need to sort. It's less likely that you need to sort because finding kth element is faster than sorting the whole array. Okay. If you missed the tournament algorithm, then yes, you did miss something. Go watch last week when I solved the majority candidate problem. We did not cover FFT. It will not be on the exam, but I just leave in the slides because it is an interesting topic if you want to go through it. Where is fast select described for this class? It is in the lectures. Okay. Common divide and conquer mistakes. Suboptimal solution, different penalties applied depending on how simple that suboptimal solution is. But a brute force solution is going to be a massive penalty. So if you don't, if you just say, oh, I'm looking for what's one to consider? Yeah, if you just skin an array when binary search is allowed, you end up with a brute force. Or even if you don't use a brute force approach, if you make an algorithm that's as bad as brute force or worse than that, you're going to lose a ton of points. So be very careful. So the first thing you should do when you look at the problem is, what is a very slow solution? What is a solution that's super obvious that I can do this and it would just be a slow solution? And at the very least, you want to beat that. So in the example of the majority candidate, a very slow solution would just be O of n squared. We compare every single candidate with every other candidate and decide which one's the majority. That's O of n squared. So we want to beat that. And I think we got to a O of n log n solution and then an O of n solution. So if you got O of n log n, you wouldn't get that brute force penalty. It'd still be a penalty, but it wouldn't be like a massive penalty. So consider what brute force is and at least beat that. On the algorithm part, the missing or incorrect base case also happens pretty often. Your recursion in your algorithm has to stop, and it has to actually return something so that you can bubble up your algorithm. So you have to make sure you give a clear base case on when that recursion stops. If you don't give any details on the splitting and branching, when you modify either binary search or you offer when you modify fast select or anything that tells you that you have to make a decision, you have to tell us how that decision is made. If it needs to be modified, if you're not clear on how that decision is made, that's like the core of your algorithm. How you're branching in binary search is the core of that modification you made. And so if you leave out all the details, you're going to lose a lot of points on that. Your justification of correctness, not explaining why you branch left or right. So if you change the branching logic and then you don't explain why you change the branching logic, you'll lose points. If you don't explain why you chose a black box, and this is particularly common for binary search, students just say, oh, I use binary search, and then they just move on, but they don't explain why you use binary search. It's pretty obvious you're doing it because the array is sorted, but it is the reason why you made that decision, and so you need to be able to state that. For the runtime analysis, ignoring your black box modification, even if it doesn't affect the runtime, is a common mistake. So that's it. Any questions on DNC before I move on to the next? I'm going to cover some general exam tips, and then I will be doing practice problems. Bing?
Thank you. You mentioned that it's quite obvious to say, oh, because the array is sorted, we can use binary search. There was a feedback from one of the TAs on the DNC practice question set, I think suggested problems. And the feedback was like, it's not sufficient to just say, because it's sorted, we can use binary search. I'm just trying to understand what's the actual expectation there.
I think it depends on the problem. Like if you're just straight up doing the binary search and you're searching for something, then you can say, yeah, the array is sorted, I can use a binary search. But you also have to explain why you're using binary search, I guess. So like, so there's two parts here, right? Why you chose a certain black box, and then what does the return of your algorithm, why does it satisfy the solution that you're looking for? So I chose binary search because the array is sorted. by adjusting the target of my binary search in this way, I am able to find what this problem is looking for, and that is my solution. So if you then just say, oh, I use binary search because they're array sorted, that's not enough. It doesn't tell me why your target is changing. It doesn't tell me why your branching is changing. It doesn't tell me why your final return value solves the problem. So there's a second part to it, but the first part on explaining why you use that black box is the one that a lot of students miss.
Right. So I think for that particular problem, it was saying like it's insufficient to just say, oh, because the array is sorted, which allows the use of binary search, you have to further elaborate on why the overall algorithm is correct in the justification, right? Not just say, hey, because it's sorted, we can use binary search, that's correct. But it's also not wrong to begin with saying, hey, binary search is allowed on a sorted input, right? Or a sorted array. That part alone is not wrong, but you just have to further elaborate on.
So it's needed, and then more details on why your algorithm solves the problem.
Right. So that part is absolutely needed, and writing that sentence alone at the beginning is not considered wrong as long as there were further elaboration on the details, right? Okay.
Correct.
Thank you.
Okay. All right. So here, Manjunatha?
A question about the recursion and the base case related. So I take an example of the homework. I think homework 2, the towers example, where we wanted to look at the recursion, right? You apply the binary search and then you go left and right. I think when we get into that level, it becomes like in my mind, I'm already thinking about the pseudocode or a code where you are branching. Is there any way to get out of it and then think in general how the recursion happens and finally you find that last answer that you written?
Yeah, so here is where I do the opposite of what I was suggesting you to do in dynamic programming. When I solve divide and conquer problems, I think in my mind, I start with base case. So try not to confuse what I say now from what I say for dynamic programming. Two different types of problems, two different types of approaches. For divide and conquer, I think to myself, okay, if I had an array of 2 elements, how do I decide which one is the right solution? Then I move up. If I have an array of 3 elements or 4 elements, how do I get myself to the array of 2 elements? And then from there, if I'm an array of 8 elements, what do I do? What decision do I make to get from there to my array of 4 elements? And that is how I build my solution. I start with the base case. If I had a binary search and I had 2 elements, right? Well, if I have 1 element and it matches what I'm looking for, then I return it. I'm good. If I have 2 elements, I can say, okay, well, what if one of the elements is matches what I'm looking for, then return it. If neither of the elements matches what I'm looking for, then I haven't found it. Now I go up to the next step. Well, how do I get to that two elements? Well, I can say from the middle, if everything greater than it can't be it, then I can just eliminate that half of my array. If everything less than it can't be it, then I eliminate that half of the array. And so I build my way from the bottom to where what my algorithm does. That's the approach I take for DNC.
Thank you. Interesting.
Yep. Stephen?
Hi, yeah, just a quick question. In like all the lectures and in other places elsewhere, it says we don't need to know FFT, but in your slides here, you mentioned like FFT is a possible algorithm that could be used. Can you just confirm if we need or not?
You can just ignore it. Just ignore it. Yeah, it's some Dr. Brittle decides to put in topics and pull topics depending on the semester, and sometimes FFT is in there, sometimes it's not. So I don't generally change these slides from semester to semester if I don't have to. So just ignore the FFT completely. If it's not this semester, so just ignore it completely, and you're fine.
All right, so we don't need to know basically. Okay.
Yep.
All right. Thank you.
Yep. Nishank?
Hi, Joves. Can you give like an example of like a good justification for explaining why the algorithm branches to the left and right, or one or the other?
So I probably covered it at some point last week in my office hours, and I will be going over additional examples this week. So I'll probably cover it again this week. So.
Okay, thank you.
Yep. All right. So general studying tips that I have. Try not to cram it all in one night. At this point, you have 4, 5, 6 days, however, whenever you decide to take exam until the exam. That's still plenty of time to study. Do not leave it till the night before the exam. This class cannot be learned in one day. It's just, unless you already know everything about, unless you would have aced the exam right now, you're not going to ace the exam studying just one night before the actual exam. Okay, it's something that you have to sort of like learn, let it rest in your head a little bit, learn some more, let it seep into your brain so that you can recall it during the exam. So try not to cram. Bad idea. Work out a schedule and stick to it. It's really easy at the early start of the week to be like, oh, I still have tomorrow. Oh, I still have 3 days. Oh, I still have 2 days. And then by the time you get there, you're never going to gain the time that you lost, that you just said, oh, I don't feel like studying today, I'll study later. So work out a schedule, figure out how many hours you would feel comfortable studying, work out a schedule, try to front load it if you can, because if you front load it and then you start feeling really good about your studying, you can decide, oh, I can take it easy the day before the exam, and that's perfectly legitimate. But if you backload it and you end up not having enough time to study, there's no way for you to kind of gain that time. Do the assigned homeworks again. Those are the ones that are going to be most closely related to your exam problems. So those that are graded. Do the assigned practice problems. Okay, so the ones with official solutions of the next priority, and then do all the suggested practice problems, which is the ones that I'm going to try to go over today. Those are also really good examples of problems that you might kind of see on the exam. Focus on the ones that's most similar to homeworks. So there are going to be some that are like, yeah, it kind of tells you and helps you understand DNC, but it's not really in the format of the homework and the practice problems that you've solved. So, you put that towards the end of your list. Just focus on the questions that look very similar to how your homework problems are asked. And when I go over the practice problems, I will point those out. I'll say, this is much more similar to a homework/exam problem. This is just sort of a mental exercise for you to understand. So I'll point those out for you. Don't spend too much time on the harder ones unless you've already studied all the other ones and you feel like you really want to stretch your abilities. I enjoy the really harder ones because I enjoy algorithms. But if I was, studying for an exam, I would rather go over the ones that are most likely to be topics covered on the exam versus trying out the harder ones. So that's just my advice. And again, I'll point. I think on the post, it says these are harder, more difficult problems than you are, intended to be able to solve, and I'm actually going to skip them so we don't waste time on problems that I don't think you need to fully understand to do well in this exam. But if you want to talk about it in the practice thread, by all means do it. And if you want, you can also tag me and I can take a look, because I actually have solved all those problems and they're mostly fun to me, but probably not what you want to do for the last 4 or 5 days before an exam. Take breaks if you need to. Do not try to cram it all for 5, 6 hours straight. Some people's brains work like that. If you're that type of person and that benefits you, by all means do it. But for most people, it's actually harmful to just kind of sit there and constantly try to figure something out for hours and hours straight. Take a break, let your brain relax, let your brain sort of work on it in your subconscious, and you'll get more out of it. Try to study in the same environment that you will be taking the exam in, and that follow-up is try to study around the same time of day that you're taking the exam in. So studies have shown that if you study at the same time in the same place that you're going to take an exam, you're more likely to be successful because your brain now associates that environment and that time with, okay, I need to focus on this information, and it'll recall that information better. So use that as a helpful guidance for studying. Study with others if you prefer. I really prefer studying with others because I feel like explaining a solution to another student really helps me fully understand it, because now I have to not only do I write the solution based on how I see it and how I would phrase it, I now have to explain it to another student, and then come exam time, I might be like, oh, okay, maybe if I wrote it this way, the TA might not quite understand what I'm writing, so I will explain it more simplified, or I'll understand it in more, I'll explain it in a more detailed manner. So studying with other people is really helpful, but don't mistake other people solving the problem as you having solved the problem. A lot of students fall into that trap where the entire group managed to solve a homework problem, but they just kind of assumed they were part of that, and they end up not being able to solve it on the exam. So first, solve the problem on your own, so you know exactly what your weaknesses and your gaps are, and then bring it up with the group to sort of fill in that gap and bolster that weakness. So a super pro tip, and this is what all the TAs will tell you, is to go and see the mistakes other students have made. When you don't make a mistake, you don't know it can be a mistake. And therefore, when the exam comes, you may make that mistake that you did not make in the homework because you didn't even think about it, right? So when you go to the regrade threads, even if you got a 20 out of 20 or 10 out of 10, seeing what other students make, seeing the mistakes other students make, you can avoid those same mistakes on the exam, right? Like, oh, I guess, I could have been a little bit more detailed in this. I got away with it with full points, but this student who is slightly less detailed than me lost 2 points. I guess I'm right at that borderline of possibly losing points. On the exam, let me make sure to be a little bit more detailed than that, so I don't run the risk of losing those points. So be very careful with that. And if you didn't do this, if you didn't submit a solution, you're already in the bad place. You didn't get feedback on what your solution could be on the exam, and you didn't know what points you're going to lose. You've already made a terrible, terrible mistake. Don't compound that by avoiding the regrade threads. At the very least, go see how the TAs are grading these problems so that you understand what to watch out for when you go do the exam. Okay. Some more general exam tips. So these are studying tips, but on the actual exam, here are my general exam tips. You should rest before the exam. Don't go into the exam all tired from studying. Don't go into the exam all anxious. Your attitude, your emotional state matters a lot in these sort of high stakes exams. Just like you would, for like a tech interview for a job you really, really want. You want to go in there relaxed. You want to go in there confident. You want to go in there rested. Same thing with this exam. So try to be relaxed. I know it's really hard, but you need to find a way to calm down. If you freak out during the exam or you freak out before the exam, you're going to hurt yourself. So things that you can consider is, if meditation helps, if taking a nap helps, if incense help, all those things that you normally use to calm yourself down, do that before the exam, and then go into the exam as relaxed as you possibly can. Okay, you need to slow down. A lot of points get lost because students are rushing through the exam and not rereading a problem. Reading a problem and then immediately launching into writing a solution when you didn't quite read the problem correctly, or you missed a requirement, or you missed a very important thing in the problem that makes or breaks your solution, is devastating. Don't do that. Read the problem, try to figure out what that exam question is asking, and then read it again just to verify, and then write the requirements down, and then go look at the exam problem again to make sure you got all the requirements. And this is actually a very good tip in terms of interviews. So I've done like hundreds of interviews of other people, and I now do interview mock interviews and guidance for people to do interviews. One of the things I always tell to-be interviewees is to reiterate the requirements given to you so that you and the interviewer have an understanding of what the actual question is. You can't do that in an exam because there's no TA sort of overlooking it. But what you can do is write down the requirements and then compare your requirements that you have on the scratch paper back to the problem. Make sure you hit all of them and then start solving the problem. Okay. So let's let read the problem, read it again and again. Same with the questions. You don't ever want to lose points because you know the answer but misread the problem. Okay, so read it again if you have to. write down your multiple choice question answers. You don't have to do this, but it's really helpful because what happens after the exam is that students are allowed to discuss solutions both to the written and the multiple choice questions. The multiple choice question answers are given to you in a randomized order. So you may not get, the same A, B, C, D that another student gets. So if you come in and you go, oh, I got C on number 5, and you don't know what that C is, then you can't compare your answers with other students. We do this in class. Do not do this outside of class. Obviously, that is, that is a academic integrity violation. But when the forums open back up, students find it. Most students, you don't have to be one of them. Most students find it more calming to know whether they got the multiple choice questions right or wrong, rather than wait like a few weeks for the answers to come out. And in general, students will come up with a consensus pretty quickly, whether number 5 was A, B, C, or D. And so having your answers really helps. Okay. Don't select the right answer on the multiple choice questions. Eliminate the wrong answers. Dr. Brittle likes to tell students that he doesn't think his multiple choice questions are tricky. I always like to append to that by saying it's not tricky to him. Dr. Brittle doesn't find these problems to be difficult. He doesn't find them to be tricky. We do, right? Students do, TAs do. We look at these problems, we're like, oh yeah, this is actually not as simple as you first look at it. So when you just go by the first answer that you think is right and move on, it can be a answer that kind of might make sense unless you see some of the other possibilities and you go, oh, actually, it's really asking for this. So go through each of the questions. Each of the proposed answers and cross out the ones that you don't think is the right answer, and then eliminate them to get to the right answer. Doing the other way around, you could possibly lose points by selecting something that sounds like it could be correct when a different answer is much more obviously correct. But not much more obviously, but much more correct, I guess. Okay. I like to answer the multiple choice questions first. You don't have to. So what I do is I read my written problems so that I understand what I am trying to solve. And then I'll kind of be like, okay, think about it for about, a few minutes, move on to the next one, think about it for a few minutes, move on to the next one. And then I go and answer all the multiple choice questions. Multiple choice questions are, you got it or you don't. Whereas the written problems, you get partial credit for writing, a mostly complete answer. So what happens is if you do the written and you put all your time into it and you don't properly time out your exam, you get to multiple choice questions and you start running out of time. And if you miss any of those problems, you lose points immediately. On the other hand, if you start with the multiple choice questions, feel pretty good about it, and then go on to the written, I can safely say if you had an hour to solve a written problem and you had 10 minutes to solve a written problem, you might come up with the same solution with those 1 hour in those 10 minutes. If you had an hour to go, you might double and triple and quadruple check the answer, take the time to write it, much more formally. You might even delete some paragraphs because it doesn't look, it doesn't sound as concise as you would like and rewrite it. In 10 minutes time, you might just write out the solutions as fast as you can and hope for the best. And you might get a 20 out of 20 on both of them because we're not grading you based on how long you spend on the answer. We're just grading you on the correctness of the answer. And so you can contract your time on the written problems, but still get full credit just because you realize you have to write more quickly. It doesn't quite work as well on the multiple choice questions, so that's why I like to do it in that order. It's up to you though. Some students really like to focus on the written and then move on to multiple choice questions. That's completely valid. Okay. Finally, try to enjoy the exam. I mean this very seriously. For a lot of you, this might be your final semester of your academic career. You might graduate after the semester and never take another, exam in your life. And so these are your final 3 exams, hopefully, possibly. And if so, you kind of want to have a good time. You kind of want to say, oh yeah, I remember my time at Georgia Tech fondly. I took, some exams. It was really, really difficult, but I enjoyed it because of the challenge, and I passed with an A, and I'm super happy about it. I'm super proud of it. That's the mentality you want to take out of this class. If you go in thinking this exam is dreadful, I'm going to be miserable, I'm going to hate myself, I hate everybody around me, that attitude is going to translate into your performance poorly. So don't do that. All right. That is my general exam tips. And then we will go over practical help. Any questions about exam tips? Aaron?
Yes, thanks, Jovis. So you mentioned redoing the homeworks, the assigned homeworks that we were given. I realized that some of the homeworks that we were assigned were coding homeworks. Although there's not going to be any coding on the exam, would it be helpful to do those coding homeworks in preparation for the exam? I guess, like, how would that benefit us? Or I guess maybe me going into the exam, since there will be no coding.
Yeah, so I would recommend first, if you don't think you have time to do the coding problem, I mean, they're super fun. I enjoy them. I write most of them, so I enjoy doing them. So if you don't think you have time, at least do it in a written form. Like, the questions are asked in such a way that you could write a solution into like a written homework, and then talk about it in the thread, like, hey, I didn't have time to do the programming problem, but this is what I would do if it was a written problem. And can anybody critique this? Can anybody tell me if I came to the right conclusion? So forth and so forth. Coding the problem is also super beneficial. I think they are very leak code like. So if this class is if you're trying to go for a leak code type interview using this class as sort of a learning experience, these are leak code type questions. They are designed to be sort of like a programming challenge that you may possibly see in an interview. So I think that's helpful, and you get graded on it. You get solutions. You get tests that run after you submitted it, and we also do some cool runtime testing against a model solution. So I think it's a really fun challenge. But again, you have 4 or 5 days before you want to take the exam. So I absolutely understand if you think, oh, I don't have time to do this. But at the very least, solve them as a homework problem. It's another practice problem for you to use to study.
Got it. Makes sense. Thank you.
Robbie?
Thank you, Jovis. About general studying tips, there is something I need to say. I know the syllabus said that for homeworks, we're allowed to use AI tools, and I took it to mean that we're allowed to use ChatGPT. I've been using ChatGPT to do the practice problems, and even the homeworks, but I just use ChatGPT to say to give voice to my thoughts. Like, I've been thinking of this idea. Is this going to work? But I also took care to write down, don't give me the answer, never give me the answer, or anything similar. Is that a good way of using ChatGPT, or no?
ChatGPT is allowed. I think it can be a very powerful tool in studying and learning if you do it correctly. I personally never used any sort of generative AI until I have completed a solution. So any programming problem, any homework problem that I'm trying to solve myself, I will go and fully answer it. I will get to the point where I think, you know what, I am okay with submitting this as my own assignment and get a grade on it. If it's a graded homework problem, I just submit it and see what my feedback is. If it's a practice problem, or if it's a practice problem that I'm not giving a solution, now I need to verify it. And I think ChatGPT or generative AI in general is an excellent tool for that. So I would ask the question and have it generate a solution, and then compare that solution to mine. It might not solve the answer, or it may not write the solution exactly as we would want you to in this class, but it'll give you a general approach to that problem, and you can use that to compare your own general approach.
Right.
So I think that's how.
Right, I've been using like ChatGPT just to help my understanding. I never asked it to write a solution for me. I never did anything like that.
No. And I will say that generative AI have become better and better at this kind of stuff. When it was first introduced a few years ago, and students were starting to sort of use it, and you could tell it was terrible. Like, it would give you the wrong answer, and it would give you an answer that was very obviously written by AI. And students would submit it, and they would get, bad things happen. And I think today I would actually, like I used to say, not only is it not an allowed tool, I wouldn't even recommend it. I think today I would say it's allowed. I would recommend it, but try to learn from it instead of using it to solve your problem. All right.
Yeah, just to
Jafar?
learn, basically.
Yep. Jafar?
Hello, are you hearing me?
Yes.
Yeah,
Yes.
first, thank you very much for your session. And second, I want to ask some tips about the timing in the exam. I know you already talked about it, but how to divide the time between the big problems and the multiple choice ones? So should we, for example, put, let's say, this is an hour for DNC, this is an hour for DP, and then the half an hour to MCQ, or how do you think?
The way I would do it, and this is just me, so pick your own strategy. Everybody has a different strategy. The best strategy is the one that works for you. So what I normally do is I read the problems, I think about it a little bit, maybe write a few notes, see the next problem, read about it, write a few notes, and then I move on to multiple choice questions, and I answer those the best I can. I try not to sit on a problem for too long. I just go with what I think is the best correct answer, and then I now go back to my design questions. On my design questions, I try to write a very, hey, this answer is a one that I would be comfortable submitting if my time runs out. I could write it a little bit more clearly. I could, put more words in it, be more detailed. But if my exam cut off right now, I'd be generally okay with it. And I moved on through my problem. Now, I have a complete exam. My exam, if my time cut off and got submitted, I wouldn't feel like, oh, I did my best, but I wouldn't feel like, oh, I bombed it. Now I go and I look over everything. I go over everything with, in more detail. And that's basically how much ever time I have left. So if, there was a couple of multiple choice questions that I wasn't too sure about, but I answered it already, I'll go back and take a second look. I'll put it on my note, like, review question 5 or something like that. And then I'll go and look at that. If, my DNC, I was like, yeah, I know my branching logic works, but can I, make it, make sure that it's written more details so that the TA can't possibly, misunderstand what I wrote. I'll go back and do that. The DP is much more formula. So it's like, it's very much looks like a program, right? So once I am done with the dynamic programming, I just go back and check my base cases. I check my, my ranges. You're always going your biggest risk on DP problems is going to be those like off by one issues where like, oh, I didn't quite get to my base case correctly. My range wasn't quite right. I generally try to feel really good about my recurrence on my DP before I move on to a different problem. So I would not spend 1 hour in one section, 1 hour in another section, 1 hour in another section. I would write a very solid task all the way through to give myself as much time at the end to review, and then go back and review the things I felt most needed to review. That's how I plan my time.
Yeah.
Basically,
do you think we have
3
enough
hours,
time?
We provide the time on exam that we think students should have, right? Like it wouldn't be fair for us to be like, yeah, we think students really need 3 hours on the exam, but we're going to give them 1 hour. So, I mean, yeah, my answer is going to be yes. I do think you have enough time on the exam.
Okay.
But yeah, it all depends on you.
Yep. Okay. Thank you.
Okay. All right. So we're going to go over practice problems. I'm going to give everybody a break for a little bit, but these are my dynamic programming problems. There's two possible solutions to 6.7. I might skip one of them and just do one depending on time. And then these are all the other dynamic programming problems. I think there were some problems that's listed on, that were like, these are really difficult, or, these are, very math heavy. And so I skipped those. If you need solution to those, or you need someone to verify your solution, feel free to do them on the practice threads. That is the point of the practice threads, is for students to sort of, bounce ideas off each other. So go do that. All right. Let's do 2 to 3 minutes of break, use restrooms, get drinks. I'll be right back. Some additional tips. When you take the class, take the exam, you're allowed snacks and drinks. I try not to bring too much water because you can't use the bathroom, and if you end up having to go to the bathroom, it's unfortunate. So I tend to take fruit that has high, water content, I guess it's called. I don't know. So I like grapes. I like watermelon with a fork or a toothpick. I like cantaloupe and honeydew. And I just snack on them as I take the exam. Another one I really enjoy is chocolate covered espresso beans. I think it gives you like a slight hit of caffeine as you take the exam, so that's nice. You should know your body best when it comes to caffeine. So if you need it, then go for it. But I don't recommend drinking coffee immediately before the exam because you end up getting those highs a little bit and could get jittery depending on you. So that's what I do. All right. Let us get started on practice problem. As soon as if we will be doing debug poker, we sure will. Putting up the right pages. So the solutions I will be presenting to you today are my personal solutions that I solved when I took the class and since then. So they are not considered model solutions. So there could be mistakes in them. And if there are mistakes in them, feel free to point them out. But if you go and take the exam and say, hey, Joves said all this in his office hours, we should get points back. That may or may not work. So when in doubt, follow what the class resources, like the lectures, the books, and the model solutions have given you. I'm just trying my best to provide you with another source of material. All right. First problem, hotel stops. This is 6.2. So one of the things I like to do when I solve the practice problems is that I like to put it all in one document so that it's easy for me to sort of go back to and study. The other thing I like to do is I want to write down what type of problem I think, what type of problem it ends up being. This does a couple of things. I feel like, if I want to study some LCS, I can go and easily scan all the problems I've solved and go, which one's LCS? And it starts that practice of recognizing first what the pattern I need to solve the problem, and then and then using that to solve the problem, rather than just solve the problem completely freely without some kind of strategy. Excuse me if you hear my mouth. I decided to have some nuts before coming back, and something stuck in my mouth. Okay, hotel stops with minimal penalty. You're going on a long trip. You start on the road at milepost 0. Along the way, there are N hotels at milepost A1, A2, ... AN, where each AI is measured from the starting point. The only places you are allowed to stop at these hotels, but you can choose which of the hotels you stop at. You must stop at the final hotel at distance A of N, which is your destination. You'd ideally like to travel 200 miles a day, but this may not be possible depending on the spacing of the hotels. If you travel X miles during the day, the penalty for that day is 200 minus X squared. You want to plan your trip so as to minimize the total penalty, that is the sum of all travel days of the daily penalties, given an efficient algorithm that determines the optimal sequence of hotel stops. Okay, so first thing I thought is, okay, well, this is an LIS problem. Why? Because I'm traveling across a single array. I'm not comparing to anything else. I'm not trying to fit anything into a bag or into a partition or into a sum. So it's not a knapsack problem. It's not an LCS problem. So generally, the two things when you end up with this is, it's an LIS problem or a windowing problem, because they're very similar, other than the solution. So it's an LIS problem because I'm taking some value, some calculation, and I'm moving it along with my across my my table, my subproblem table, and deciding what is the best solution at each I, and then take the final best solution at the end. So that to me is an LIS problem. Okay. So now the next question is this a O of N variant or O of N squared variant? O of N variant means that before my current I can always tell what the best solution being moved forward is. Okay. Whereas a O of N squared solution means I can stop here based on any place before me, any hotel before me, and I have to calculate what the best solution is all the way back to the beginning. Okay, and so if you consider that, then this to me is a O of N squared solution, because I may not know what the best hotel to me to stay to be previously stayed at from here is, right? Like, I'm not going to stay at a hotel that's 10 miles before me. I'm not going to stay at a hotel 20 miles before me when there's a hotel 200 miles before me. And so I would think, oh, yeah, I immediately know which hotel I should have stayed at last and the hotel I stayed at here. But depending on all the hotels before this, the hotel right before me that's 10 miles away, even though it's not a good idea to stay at that hotel and this hotel, it might have been a good idea to stay at that hotel regardless, because all the other previous hotels, made sure that that was the optimal solution. So without being able to tell what the optimal solution based on the very previous hotel, I have to look at everything. So this to me is an O of N squared approach. Okay. So with that all in mind, I will present to you what I have as a solution, and then we'll walk through it. Okay. All right, so the first thing I want to do is restate my problem as a subproblem definition. So let L of I be the minimal penalty possible for traveling between from 1 ... I. Okay, that is my subproblem part. I don't need to explain how the minimal penalty is calculated. It's also already in the problem statement. I just need a way to reference it. I have my my subset of my input, and that's it, right? Now, the next part, important part is, do I have to stop at the Hyatt hotel or not? Now, you can try it different ways. You can try it with stopping and without stopping, and kind of seeing which one works out and which one is correct. But our problem statement says you must stop at the last hotel. And if you must stop at the last hotel, if I was trying to calculate the ith hotel as if it was my final hotel, then I must stop at the ith hotel if I'm doing I-1. And I'm saying, okay, well, what if that was my my subset, my subproblem, and that was the final hotel I need to be at? Well, then I should stop at that too. So that kind of gives you an idea of like, okay, well, if I have to stop at the last hotel, I should calculate what the penalty is for stopping at every single hotel, or the best possible penalty for stopping at every hotel. Okay. So that's why I start with that. Okay. So then I am going to define my my recurrence definition. There's a few parts of this, and it's kind of confusing, but I'll try to highlight the parts that you should be able to focus on. Okay. So first, where's the min coming from? Okay. So first, I need a thing that states my penalty. My penalty is 200, right, minus the total distance between some I, which is the one I'm at right now, and some j that I've chosen, which is a hotel before me, and I'm going to square. That is my penalty equation, okay? That's stated right here, okay? 200 minus x squared, where x is the number of miles traveled. Number of miles traveled is between my current hotel and the hotel that I said was the best one before this hotel. Now, I have that. I need to take the T of j, which is the penalties I paid up until that hotel, plus the penalty I have to pay for traveling the distance between this current hotel and that hotel. Great. And across this, I want to minimize it, right? I want to minimize this penalty for some j, and j has to be between 1 and I-1. I can't stop. I can't stop. I can't calculate the penalty for a hotel after me. And it doesn't make sense for me to calculate a hotel to, say the hotel I'm at is the hotel I stayed at previously too, because then no distance is traveled and there's a terrible idea. So this is my equation for my penalty, the best I can do at I. Okay. There's a caveat to this problem in that this is not enough. If I only stopped with this would be able to solve for the most general case. However, there's a situation where if I'm at the 0th marker, right, and my first hotel is, let's say 100 miles, okay, and my second hotel is 50 miles, and my third hotel is 50 miles, okay? My best possible decision at the very beginning is to stop at the third hotel. It's not to stop at the first hotel and then try to stop at the third hotel, or the second hotel and then stop at the third hotel. It's to stop at the third hotel so I minimize my penalty. In that case, I don't have a previous that I want to calculate from. I don't have, when I'm at 3, I don't want to calculate it from 1 or 2. I want to calculate from 0. Unfortunately, I don't have a 0th, I don't have an A of 0 that represents 0. So what I'm going to do is I'm going to say is, well, I'm going to take 200. I'm going to subtract the distance needed to get to A of I, and then I'm going to square it. So this is the penalty if I only stopped at 3 as my first stop. If I have no stops before it, 3 is my first stop. This is the penalty. Now I compare it. I compare my penalty of what if this was the first hotel I stopped at versus what is the best solution I could have had if I stopped at a previous hotel. And the minimum of those two is what ends up being your answer. Because I don't know if the third hotel is going to be at 200. I could have like 100 hotels in between the 0th marker and the 200 marker, and I have to ignore all of those and try to stop at the at the 101st hotel. So you need both of these pieces to combine for your entire recurrence. So once you have that, you don't need a base case because this kind of solves your base case. You could also use this to do a base case. Like your base case could be like for I don't know, I to n if your hotel is less than. It'd be really awkward. You could do it. You could do it as a base case. I prefer to do it this way, but you could set up the first X hotels as oh, this is within 200 miles, so you pay this penalty on all of those, and then you start calculating after that, because then you have previous hotels to sort of base your logic on. But until then, I think this is just the better way. So then the number of subproblems I have is it is a one-dimensional array. So it is O of n, right? My array is a size n, and my table is a size n, and is one dimensional, so T of n. But how long does it take for me to fill in this table? It's not to say that the number of subproblems is the exact same runtime to fill in that table. It is the floor, but I need to consider what the amount of time spent calculating each of those subproblems are. Turns out it is O of n, right? Because I have this additional loop right here that goes from 1 to I minus 1. This is also O of n. Okay, so the two O of n multiply, and my runtime is O of n squared. Okay, and then my final return, because I am stating that at the ith hotel, that is the minimal penalty to travel to that hotel, and the question is asking how much penalty do I have to pay to stop at the nth hotel. My final return is the final value, which is T of n, and then the runtime to extract that return is O of 1 because it's only one value. Okay. All right. Questions? Apratam? Apratam?
Hi. Yeah, I have a quick question. So you said that the recursion is minimum of 200 minus AI square, but what if AI is at 250 or 300? In that case, this wouldn't be valid, right? So we would have to add another condition over there where the AI is less than 200?
Nope. You can always calculate it. I mean, it's all of 1 to calculate, so it doesn't ask your runtime. You can always toss it out, right? If it's 250 and for whatever reason, your the rest of your the rest of your checks is better, then you take the better solution. But it doesn't matter, right? Because if I said, I also could have this condition. What if your first hotel was 400 miles away and you have to stop there, right? So you can't just say like, oh, if it's over 200, don't consider it at all, right? What if the first hotel you could stop at is 400 miles away, and that's the way to decrease your penalties?
No, I was considering more if it's worst. For example, if it's 250 and the first hotel is like at 100, then in that case, the only solution would be to go to 100, then 200, because you can't go more than 200, right? But if it is at like 250, then
you can go more than 200. You're allowed to go more than 200 miles.
Are you allowed to go more?
You pay a penalty for going over 200 miles. You also pay a penalty for going under 200. So that's why it's 200 minus x squared. Because either going less than or more than 200, your ideal is 200, but anything above or below is a penalty.
Got it. So you're allowed to go beyond 200. I thought it was like we had to stop at 200. Thank you.
Gotta read the question again. If this came up in the exam, that would be issues. So reread, like you make those assumptions, which is fine. You should, and then go back and read the problem again to verify that those requirements that you thought you gathered when you first read it are correct.
Got it. Thanks.
Yep. It's also a good practice to like be suspicious when you read a question. Your initial assessment that oh, you can't go over 200, could be true. But why 200 minus x squared? Why do we square it? What is the point of having a 200 minus x squared? And the reason for that square is that we want to treat less than 200 or more than 200 miles traveled as a same magnitude of penalties, and that's why you square that number. So be suspicious of any part of the problem that doesn't make sense, and it could indicate that you misread something. Suram?
Hi, coming off mute. Hi, Joves. I have a question about setting up the base case where I is equal to 0. Are we allowed to do that in this case? Because I feel like it's kind of tricky because the allowable ranges are from 1 to n. So
You
and yeah, go ahead.
you are allowed to define your table with any beginning and end as you please. You are not allowed to modify the input. So you cannot say I have a of 0 equals 0. That would have made this question easier. I agree. But you're not allowed to do that. So you have to either find a way to sort of gate around that idea or do what I did, which is, I will always calculate how much it is to travel to this hotel directly. And then I will just compare that against, my actual recurrence. Either way is fine, but you can't say a of 0 equals 0.
Okay, that's fair. And then the follow-up is how did you, I guess, think about setting up the first condition where 200 where you go directly to the hotel and skip all the others? That intuition seems a bit like something you would have to think about in the edge cases.
Yeah, so I came up with this recurrence first, right? This recurrence right here, right? This is pretty standard, and hopefully all the students were able to do this. And then I just worked back from there. I said, okay, well, if I had an example and I worked back from it, does this make sense? And then I realized, when I was doing okay, well, what happens if my first hotels were all under 200? I don't want to stop anywhere until I get to the 200th hotel, but I have nothing to compare it back to, right? So this was during my base case idea. I can say, okay, well, the base case of T of 1 is, my T of 1 was going to be this, right? This is always going to be the cost of my first hotel, no matter what. No matter whether this special edge case or not. This was originally my base case. T of 1 is equal to 200 minus A of 1 squared. From there, I said, oh wait, but what happens if the second hotel is also? What if the first hotel is 1 minus? Do I want to stop there? What if the second hotel is 200? Well, then the second hotel becomes my base case. Well, what if the third hotel is 200 and the first two hotels are 50 and 100? Well, then my third hotel is my base case. How do I represent that in my recurrence? It was just okay, well, I know how the base case should be calculated, 200 minus wherever that location is squared. How do I represent that as calculate that for all, however many hotels until I actually should stop and then continue my recurrence from there? And so my idea was, well, I'll just calculate it for every single hotel and just see if that's a optimal solution or not. So that's how I arrived there. Getting to the recurrence first, getting to the base case, realizing that base case doesn't hold if T of 1 is some minuscule number, and then if 2 is not a minuscule number. So then I realized my base case actually has to be considered for my entire list of hotels. Hopefully, if you were to solve this problem, you would have gone the recurrence and you would have at least gone the base case. And with those two parts, I think, even if you lost points, it would be, it wouldn't be all of your points. It would be some fraction. But getting that final piece is where how you get the full credit. Anna?
Hi, is it me or was it someone else? If it's me, I was curious where the case where I is 1, so the first time it iterates, so we won't enter into J, right? Because there's no,
it's just a for loop. Yep.
Yeah. So we can do the min over an empty set. That's okay.
So I think a min over, generally, if you're just taking the min as a single statement, you should have an otherwise. But I think the min of two things where the second one doesn't have a this statement right here doesn't have a proper return because this right here doesn't have a proper return. But I do have this part right here, which is always going to have a proper return. The min should just take the min of the only value that has a proper return. So it would just take this. But if I was just to take if this part right here didn't exist and I said min across this, and I know that this may not be solvable, I would say otherwise 0 or something.
Okay, that makes sense. Thank you.
Yep. And I'm sorry, I did skip someone. Mitchell?
Hey, Joves. Just a quick question, somewhat building off of the previous question. To kind of avoid that issue of getting the min over an empty set, I opted to not use a min on that second part of T of J plus the penalty of traveling from J to I. Now I know that that inner min will give you the optimal answer for that set of J. If we decided to omit that min, we still end up doing the same comparisons. We're just using that outer min instead. Would that, and it looks like it still gives this the same answer. Would that still be technically correct?
Yes. I believe that is true. Yeah. So instead of,
because that inner min gives you the optimal answer for the previous values. So you end up using that outer min only once, where you do a comparison of traveling directly there versus the optimal answer for previous solutions, where the outer min, if we
I would
remove
have
the
to see
inner
the
min,
exact recurrence. I would have to
Sure.
see the exact recurrence to decide if it's correct or not. So like, if you want, you can post it in the practice problem thread and then just ask for feedback.
Perfect. Okay. Thank you so much.
Yep. Anika?
Hey, so I think the wording of the question kind of threw me off because it says ideally like to travel 200, but I think you just said that you're allowed to travel more than 200. So why can't you just say that you're just doing it in one trip and going straight to AI or AN?
Because you pay a penalty. You're minimizing the penalty. If you travel from 1 all the way to N, and it's like 1,000 miles away, your penalty is going to be huge. Every time you stop, you reset, and you may not have to pay a penalty the next time.
But is it like a negative penalty? So then is it still the minimum? Like,
no, it's a positive penalty, and you're minimizing the positive penalty to be the smallest penalty possible. So like, if you end up with some huge number, you're gonna have to pay that penalty, and that penalty is not what you want.
like if it's like a 500-mile thing, don't you just get a negative number as your penalty?
Well, you square it, so then it becomes a positive.
Okay, so you still have to square it. Okay, got it.
Yeah, so 200 minus 500 would be negative 300, and then you square it, and it's like 90,000, right? So it's like some giant penalty. Whereas like, if I stopped exactly at 200 miles along the way, then I don't pay any penalty. So you have to consider what happens there.
Okay, got it. Thanks.
Yep. All right, I got like a billion hands. I really need to get going a little bit, so I'm going to answer 2 more questions, and then we need to move on. Aaron?
Thanks, Jovis. So I noticed that some problems that were given don't specify the domain of numbers that we're working in. So for example, like, is the input that we're working with in this set of natural numbers, integers, reals, or anything like that? Will we be expecting that same on the exam, or is it up to us to determine the kinds of inputs that we're...
So I would think, one, it'll either be given to you if it matters, or it doesn't, if not given to you if it doesn't matter. This one doesn't matter, right? Like 200.5 and 200 would work the same way in this problem.
Got it. Okay, that makes sense.
I will say that like the problems are designed to also be kind of obvious in sort of its domain. Like, if you start, first of all, I don't think negative values would affect this. Don't quote me on that, but you shouldn't expect negative values on a problem like this, right? Like, it tells you that you're traveling from someplace to someplace, and you start with 0, and then there's miles along the way. So you should not be expecting negatives on this problem. Things can change on like on other problems that doesn't like if I just tell you numbers, you should expect it to work with negative numbers unless like the problem statement makes it like not logical to work with negative numbers. Like this one I wouldn't expect negative numbers.
Got it.
All right, Jafar?
Yep, thank you very much. Another time. So finally, a small questions here. Okay, I understand, but mathematically, it's not correct to write it like that, in my opinion, to have j going to -1, starting from 1, and then I going from 1, starting for something. So j between 1 and 0, I don't know if it's correct or not to write. And you are also telling me we cannot define a0 because in my when I was making it, I defined a0 equal to 0, and then I got the first item done, so it's only the minimum of t of j plus blah blah, where I also define t of 0 is 0. And if I cannot do that, then I will need to start j from 2, and then to define t of 1 as a base case.
Right. So there was a lot there. One, yeah, you can't redefine the input in this class. And two, j from 1 to 0 is allowed. It just means that it doesn't run. It's actually mathematically fine for these type of statements to exist. And
okay,
if you have a different solution starting from t of 2, it could work. I don't know. So I guess I post those to the practice threads and get feedback from your from other students.
Yeah, basically it's the same as this one, but I'm defining t of 1 and then starting j from 2, so it's easy. So j starting from 1 is only the first item, so I'm defining t of 1 is equal to 100 minus a
I'm
of
not gonna, like I said, unless I see a solution, I can't tell you like,
Yeah,
oh yeah, that
yeah,
works,
okay,
and then you
understood,
go to the exam and say, yeah, I said it, but I didn't
Understood,
actually
yes, yes.
see it. Yeah, so just
Thank you very
just
much.
post it in the practice with. Yep.
Yeah, okay.
All right, I'm gonna move on to the next problem. Sorry for all the hands. Maybe the next one will also let you ask a question. Okay. So problems called McDonald's. McDonald's is considering opening a series of restaurants along Quaint Value Highway, QVH. The end possible locations are along a straight line, and the distance of these locations from start of QVH are in miles in increasing order, M1, M2, ... Mn. The constraints are as follows. At each location, McDonald's may open at most one restaurant. The expected profit from opening a restaurant at location I is P of I, where P of I is greater than 0. So you always make a profit. I equals 1, 2, ... N. Any two restaurants should be at least k miles apart, where k is a positive integer. Give an efficient algorithm to compute the maximum expected total profit subject to be given constraint. So you are told you actually cannot open a restaurant within k miles. This is different from the last problem where you are allowed to travel more or less than 200 miles. You just pay a penalty. Here, it's saying you absolutely cannot open a restaurant within k miles of a different one. Okay, so so when I looked at this problem, I thought, okay, this is also a problem where I am comparing a input array to itself. I am considering the maximum something along this array. I'm not trying to fit anything into a bag, partition, or subset sum. I'm not trying to chunk up my problem into windows. And so this to me was an LIS, right? I'm also not comparing two different arrays. So LIS made the most sense. Now, is this an O of N LIS or O of N squared LIS? I'm going to present to you two different answers. The first answer is what we would have expected you to do. And the second answer is a better solution, a faster solution, but it takes a little bit more insight. So if you see my first solution and you say to me, oh, actually, I have a better solution, I am going to immediately mute you because I already told you I have a second solution that will come. Okay. So when you first look at this, the naive or simple approach is to say, okay, well, at each location, I need to know what my previous best location was and whether I can build this location or not. If my previous location is far enough from me, I absolutely will build this location because there's no reason not to. It's just free profit. If my previous location was too close, I now have to consider, well, was it better to build the previous location or is it better to build this current location based on something that's far enough? So I'm not going to include A of I because, or is it A of I? What is the array? whatever the array is. I'm not going to always include the location because I may or may not have a better profit with or without it. But I do have to consider what my previous best was. So the general approach, I don't want to call it naive because it's not really naive. The initial approach is going to be all n squared. Okay, go over it. I'll walk you through it. All right. T of I equal the maximum profit obtainable with possible locations at m1 ... I. Okay. This tells us that what is the maximum profit? Doesn't matter. It's already declared. It's already defined. How do I what's my subset that I'm looking at? Oh, it's m of 1 ... I up to I because I'm doing I. But do I have to build a restaurant at this location? Nope. So I'm not going to say that it has to include. Okay. A recurrence definition. Again, you can start here, but I like to start with the recurrence first and then work my way to my base case. So my maximum profit is going to be some j plus my current profit. And the requirement for that is that my m of I, my current location, is greater than or equal to my previous location plus k miles, right? So I'm at least k miles away. So that's my requirement. This is where I'm trying to maximize. And then this is all the my range of all the things I'm looking at from previously. Okay. So now from here, okay, I once again have to consider what happens if I only build this restaurant. If I have a restaurant at mile marker 1 and I have a restaurant mile marker 2 and I have a restaurant mile marker 3, and they're all within k miles of each other, the best one is going to be whichever of those three has the best profit. So I'm going to take the max of if I was to consider only building this restaurant. Okay. So this is very similar to the previous problem where I have to consider that my first restaurant I build is all too close together and I don't know which one to pick. Okay. The other part I have to consider is, well, this is what happens if I do have to build a restaurant at my current location. But no matter what I can get for building this location, I might not be better than skipping it. So I possibly could just skip it and just based on what my previous solution was. Okay. So this is my T of I minus 1. Whatever my best previous solution was versus what my best possible solution of my current location is. Take whichever one's better. Now, the number of subproblems is O of n, right? I have a one-dimensional array. My one-dimensional table. It goes from 1 to n, so it's T of n. The runtime to calculate that is additionally multiplied by this 1 of 1 to I minus 1 j with j in between, so it's O of n squared. The final return, because I carry my best solution all the way forward, is O of n, and the time to extract that is O of 1. Okay. Any questions about this particular solution? Anasado?
Hi. So my question is, if we had, depending on how we define our recurrence, right, or like a subproblem. So if we have a solution where we included I, so we don't carry over the previous best solution, so we'll still have number of subproblems to be O(n), runtime to be O(n) squared, but then the final return and the runtime to extract the return will be different because we were taking the max, and then the runtime to extract the return will be O(n). So in a context of an exam, would we lose point because like our runtime to extract the return is suboptimal?
No. As long as your overall runtime is optimal, as long as your extraction works, and as long as your runtime matches that extraction, you'll get full points. So we care about the overall final runtime. So we don't care if your extraction is suboptimal.
Okay, thank you.
Yep. All right. Anika? Oh, sorry. No, sorry, Matthew. Anika.
Yeah, hi. So can you explain or try to explain one more time, what is the key thing you're using to determine whether you want to include I in this current iteration or not?
So the idea here is that when I am considering this location, right, whether I need to build a restaurant or not, I can either build a restaurant and then say, okay, well, what is the best profit I can make, including building this restaurant, right? And then if I try to move forward with that, what I'm going to find out is that every time I look back, I may lose out on getting the best solution if I don't build this restaurant and I just build the previous one. Now, that's not to say that this actually doesn't work. I think there is a way to make it work that you always include the current location. I think you just end up with a solution that has to look at the current one and the previous one and compare what the best profit was, or possibly all the previous best. So I think if you took a max across your entire array and extract that, I think it actually does work. So in some problems, they both work. In some problems, they don't. It actually depends more on how you write the solution, whether it needs to be included or not.
Got it.
Yeah. Because I think I think, and again, I need to work this out. I think this problem, if I was to take this and I didn't do this part at all, and right? So now I don't carry forward my best solution. I am going to just care about my current location, which is given to you by this recurrence, right? And then here, instead of saying, oh, I'm just going to return T of n, if I return max of T of n, and this takes O of n, I think this still works. I think that this version also works. I don't know if that helps answer your question. I guess the thing is, it depends on your solution whether you need to include I or not. Sometimes you absolutely have to. Sometimes you can or cannot, and sometimes you absolutely can't include it.
So nothing's immediately standing out to you when you read an LIS problem on whether to include or not. You kind of have to work it through.
Yeah. Yeah.
Okay.
And honestly, you could start with the recurrence, right? Like if I started with the recurrence and I ended up with this, and I said, okay, yeah, this will give me the answer, I would have written my subproblem definition a little bit differently. But if I go, yeah, you know what, I need to compare with the previous best and just decide to carry that forward, I would write it without including I. So it really it depends. All right. One more question, Anika.
Yes, I had a really similar solution, but quick question on the subproblem. So would we lose points if we wrote it like this and didn't include the K condition in the definition?
Didn't include the K condition. Oh, in your subproblem definition?
Yeah, like do you have to put that in that the
Nope.
without two restaurants?
Because nope, all those requirements are stated within the problem itself, but
Okay.
you're just telling you what it is you're looking for, what subset you're looking for. You're looking for the maximum profit obtainable. How do you do that? Doesn't matter. It's already in the problem statement. What restrictions you have doesn't matter. It's already in the problem statement. We don't the reader's not going to forget everything about the problem statement just by looking at your solution.
Okay, so we just need to include the subset part, right?
Yeah.
Okay, thanks.
All right. I know I have 2 more questions. Keep your hands up. I'm going to present the second answer, and you can maybe ask questions there too. All right. So a second solution that is a little bit more complicated, but a little bit more optimal. Not a little bit more. It's like a lot more optimal. Is this one. So we're going to take 2 tables. Our first table is going to track maximum j such that m of I is greater than or equal to m of j plus k. Okay. What this is saying is that at any given I, I'm going to find the restaurant that's closest to me that is a valid, still valid. So it turns out that you don't have to look back at every single restaurant to see what the best previous profit to build at this location at is. You only have to look back far enough such that everything else before it is no longer a decision for you. Because once you find a restaurant that's close enough, that is going to have a higher profit than every restaurant before it, and that is where you're going to be considered. Okay. And so you take the maximum j such that m of I is greater than or equal to m of j plus k, and then your t is still the same, maximum profit obtainable with possible locations of m1 dot dot I. So then we're going to start our recurrence. Our s of 1 is equal to 0. Okay, so at the very first location, the maximum j before it is 0. T of 0 is 0, so the same as the top. So now we're going to first solve for I. So s of I is equal to I minus 1. Okay, if my previous previous location j is too close to me, okay, sorry, it's far enough from me, then that's the location I want to track. But if that location is too close to me, then whatever location was far enough from the previous location is also far enough from my current location, right? Because my distance is only going to grow. So if I didn't get far enough from the I minus 1 location, then whatever I minus 1 location considered to be a far enough location is also still far enough from my current location. Okay, so that's how I built I. And then from here, instead of doing checking back all the previous houses, all I'm saying is that, okay, my maximum is either build a location, right, which is the t of the previous closest location that's allowed plus my current profit versus the profit of my previous location. And so there, I now have an O of n number of subproblems, same as before, but to fill out that table, I no longer have an additional loop here, so it's also O of n. And the final return is, again, my final value, O of n. And so the time to extract that is O of 1. So this is an O of n solution versus O of n squared. Okay. All right. Questions? Manjanatha?
Joves, can we also think in terms of the knapsack when you say the current profit and the profit from K location back? Can we do? Can we take the Kth location profit and the current profit and then propagate it further? I mean, I didn't think through entirely, but can we reimagine in terms of the knapsack for this problem?
You can try and then post it and see what students say. I would not have tried to do knapsack with this, and I don't know if I don't know what the knapsack solution to this would be because I didn't try it.
Okay, thanks.
Yep. Okay, the cache.
So I'm trying to understand the S table here, especially the recurrence. So we are saying that if the distance is less than K for
So
for
yeah, let me try to write that. Okay, so if m of I, right, is far enough from the previous location,
yeah,
right? So that's what this means, okay?
Yeah.
Then my closest location that is allowed, right? So it is the closest location that is allowed is I minus 1. I've decided that I minus 1 is far enough from my current location that it's allowed.
Yeah.
If it's not allowed, then whatever location was allowed for the previous location is also the location that is allowed for my current location. Because I've only gone further away, I didn't get far enough, and therefore I can just do S of I minus 1.
Yeah. So S of I minus 1 is basically a location that is at least K miles away from I minus 1, right? But there could be a location between those two, right? Like between I minus 1 and S of I minus 1. That could be another location. Which could be slightly more than K compared to I, even though it's not slightly more than K compared to I minus 1.
So let's see. I'm trying to think. So if I So if I have a location.
So if we have, yeah, let's say 100, 200, 100, 150. If we take an example, 100, 150, 200.
Miles apart?
Yeah, I mean 100, 150, 200, and 250. If we take those four, I think
so if the 100 so here I would say my answer is 0. Here, since I'm only 100 miles apart from there, I would say this is 0. Because it's this previous answer. But here, I'd actually want it to be 1. Because I'm 200 miles. Yeah, I think you're right. I think there might be a mistake with this.
Okay.
How do we reconcile that? Okay, I'm gonna think about this, and then I will hopefully give you guys a more satisfying answer. Sorry about that. I actually changed this answer recently from what I had, because the way I wrote it was a little bit more confusing, and so I changed the way I wrote it, and I think I might have made a mistake in this. So I will cover this. I'll figure this out afterwards, and I will give you a better solution in the office afterwards. Sorry about that.
Yeah, thanks.
Okay. Georgie?
Hey, thank you. I have 2 questions. One, both of these solutions are considered correct for the exam, right? Like we are not gonna get points deducted if we come up.
Not this one, because there's a mistake. But yeah, if this was correct, then it depends on the question. I think it depends on how difficult we think the optimal solution is, like how out of the way you have to go for the optimal solution versus how naive the non-optimal solution is. It depends on problem to problem. I would not say that if there is a O of n solution versus O of n squared, O of n squared is always okay, or O of n is always expected. I think it depends on the problem, and it actually takes calibration between all the grading TAs.
Okay, makes sense. And one more quick question. For these examples, like when we have 100, 100, 150, those are not input values. Those are current hotel minus previous one,
Yeah.
right?
Yeah.
Okay.
Yeah.
Thank you. That's all.
Yep. Aaron?
I think there's somebody in front of me.
Yeah, Georgie just asked a question. I think his hand's just not down yet. So I think it's your turn.
Oh, there was some. Okay, sorry. So just a general question. I guess, would you have any advice on like identifying when is the right time to use an accessory table for something like this? Since we're used to just using one table for like answering questions like this normally. I guess that's kind of where I'm having some trouble.
I generally fall upon it if I decide that, hey, a secondary piece of information is important in doing this, or a secondary piece of information is needed. I generally don't go into the problem thinking I need a secondary table, or that I don't make that decision ahead of time. It just comes to be when as I'm working through it. I was like, oh yeah, I need a secondary table because I need a second piece of information.
Got it. Thank you.
Yep. All right. Let's move on to the next question. What's the next question? It is peppering checker table.
What? I think you'll like
Peppering a checkerboard. Let's see. All right. We are given a checkerboard which has 4 rows and n columns, and has an integer written in each square. We are also given a set of 2 n pebbles, and we want to place some or all of these in the checkerboard. Each pebble can be placed on exactly 1 square, so as to maximize the sum of the integers in the squares that are covered by pebbles. There is one constraint. For a placement of pebbles to be legal, no 2 of them can be on horizontally or vertically adjacent squares. Diagonally adjacency is fine. So part A says, determine the number of legal patterns that can occur in any column in isolation, ignoring the pebbles in adjacent columns. Okay. So part A, we take a look and we say, okay, so we have different what is in rows, right? Okay, 4 rows and columns. Okay, so we want to do in 4 rows. Okay, so let's see. So as long as they cannot be next to each other, right? We can just kind of try them out. So if I have one here, then these cannot have a pebble on them. X means a pebble, 0 means no pebble, or O means no pebble. So that's one configuration. If I have a pebble here, can't have one there, I can't have one there, and so forth and so forth. So you just kind of draw these all out. So I can have one here, none there, none there, none there. That's also allowed. I can have none there. That's also valid. And then, oops. That's also valid. And then finally, you can also just have nothing. So that, I think there's one more, right? Yeah. That's also valid. Yep, that looks right to me. All right, so we got 1, 2, 3, 4, 5, 6, 7, 8. So those are my 8 configurations that I can consider. Okay. And then next part B, call 2 patterns compatible if they can be placed on adjacent columns to form a legal placement. Let us consider subproblems considering of the first k columns 1, k, n. Each subproblem can be assigned a type, which is the pattern occurring in the last column. Using the notions of compatibility and type, given O of n dynamic programming algorithm for computing an optimal placement. So what it's saying is that if I take any 2 placements, any 2 types, I can decide whether they are compatible or not by being next to each other. So for example, these 2 patterns, these two patterns right here are not compatible. These x's are horizontally next to each other. These 2 patterns are compatible because everything, we've determined that each of these patterns by itself individually is allowed. Let me just use this instead. But these 2 are allowed together. These 2 are allowed together. These 2 are allowed together. These 2 are allowed together, and so forth. I'll be right back. Hold on a second. Sorry about that. Dog was yelping, didn't know what it was, but because he wanted to go outside. All right. So these, you can decide that these are compatible because they can put next to each other. Okay. So then what we want to do is we want to set up our board of all these columns such that we maximize the points. And we know what the points are because there's numbers on this board. And then we are trying to figure out what the best solution is. So the approach to this is also LIS. The idea is that I want to maximize my points across my patterns. And my restriction is that I can only put patterns next to each other if they are compatible. Okay. So this is LIS. And the question is, well, what is my, am I comparing against O of n look back or O of 1 look back? If for every single I calculate out what the best possible solution is for every single possible pattern, I can then move on to the next column and say, okay, well, based on what I know of all the previous patterns and what their best solution is, what is the best solution for my current column based on all possible solutions? And we keep carrying all of this forward until we know what the best possible pattern is at the end. And the reason you can do that is because the number of patterns are limited. If these were n patterns, you would get a really, really large runtime. But because there's only 8 patterns and 8 is a constant, our runtime to check every single possible pattern between the previous one and the current one and getting the maximum score is actually O of 1, right? So that gives us a O of 1 look back, even though we are checking multiple patterns. All right, so what does that solution look like? All right. We're going to declare 2 helper functions, which is perfectly allowed because we're basically told what these helper functions do. Let score of ij equal the sum of integers at the ith column for pattern j. Okay, so I don't know what the values of those columns are. I'm just saying they're provided to me. So for the ith column for some pattern j, what is the score of that pattern? Let the compatibility or compatible helper function be defined as already given. K and J are true if K and J patterns are compatible, false otherwise. Right. So given 2 patterns, check if they're compatible. So then my solution, what I'm looking for is let T of ij is the maximum sum possible from column 1 ... I, ending at the ith column using pattern J. So I need to keep track of all the different patterns and what their score would be if I use that pattern, and then keep moving that forward. And so I have a T of ij. Okay. My recurrence definition. So again, I like to start with the actual recurrence, and so that is this right here. Okay. So I'm looking for the max of this, such that T of I minus 1, so the previous score, and the current k, such that k is between 1 and 8, so I have 8 patterns to look for, such that my previous pattern and my current pattern is compatible, such that the score is dependent on what the previous pattern was and what the current pattern is. The score of my current column using that pattern. Okay, so J is the pattern, I is my current column, I minus 1 is my previous column. So I'm trying to find what the best possible score is for this column for every single pattern. Because if I just pick a pattern and I say, okay, pick whatever the best score is, the pattern that I pick may badly influence my next column to not try to maximize the score. So I always have to keep track of every single pattern so that my next pattern can use that in its decision making. Okay. And so with that, my I goes between 1 and n, my j goes between 1 and 8. Remember, there's only 8 patterns for me to search through. And so my number of subproblems is O of n, because I have n subproblems here. So even though j is a 2-dimensional array, that 2-dimensional array is fixed at a size 8, so it's still O of n. The runtime to fill my table is O of n, because again, this for loop right here from 1 to 8 is a constant for loop. Does not change my runtime. 8n is still O of n. So that's my O of n. What is my final return? My final return is my final column and the maximum of all the patterns I have computed. It is not a single known answer until I check every single pattern to see what that ending pattern optimal score is. And then my runtime is all of 1 because I'm just I am just doing a max across 8 numbers, which is a constant, which gives me all 1 runtime. Okay. Questions about this problem? I'm gonna. Can I move this? Hopefully you guys have the question open and just read this. All right, Jafar?
Hello, another time. So
Hello.
my question here, maybe I made a fatal mistake here that I did not recognize that it may have negative numbers. Because with only positive numbers, this exercise is very simple. You only take one of 2 patterns, so either 1 0 1 0 or 0 1 0 1, and then you compare to the other, and that's it.
Why? I don't think.
If it is all positive, then it's maybe either this or that. This is one of the maximum if we have only positive integers. But why we have
I don't think it
negative
matters
integers?
whether. I don't think it matters whether there's negative integers or not. It should just work. Because you're
This
taking the
will work
score.
for positive. This will work for positive also. But if the easiest one for the positive one, we only have 2 patterns. So why you should not take for the first pattern for you, for example, you take the first one and then the 3 others you did not took them. If you have only positive, you should take one of them because it will update the store to a better score. So the patterns here are 1 0 1 0 and 0 1 0 1. That's it. So either you take the first and the third, or you take the second and the fourth. Because for anything, it will always give you a better score. Either it's 0 or it's 1, 2, 3. So you are adding something. If you have negative, it makes sense. So to not take one of them. But if you don't have negative, no, that's it. So it's one of 2.
I'm sorry, I'm not understanding how negative values change the solution at all. I think negative values work, and I also think if this was only positive, it would be the same solution.
Why you are taking 8 patterns for if it is only positive?
Why am I taking 8 patterns? Because the numbers are completely. I have to consider all 8 patterns. Why wouldn't I consider all 8 patterns? Which patterns would I be able to eliminate?
The first one, for example, the fourth one, for example, and the before last one, for example. So those are 100% we are eliminating them. Why you are not taking any one of them? You can't take it. I don't know.
I see.
Yeah, I don't know if I'm talking something very, but it's a fatal
No,
mistake.
I see what you're saying, and yeah, it is a slight miss on the understanding of this problem. So suppose let me see.
There is one edge case that I can consider also, but I don't know. I hope that I don't miss this understanding in the exam because then the full problem is lost.
I see. You're saying some of these patterns are not maximized.
I can give you a counter example.
Hold on. Because it runs through, it runs multiple multiple deep, right? Let's say I have a column that's like right here. I don't know what this is going to be, right? Let's say here I have this as the best solution.
You cannot take this one. Yeah.
Right. So, oh, you can't. So that's the only one I can do, right?
Yes.
Right. So if that's true, I feel like some other pattern. So like you're saying we can eliminate this one, right?
Yes.
Okay, so if we have so if I have this allows for this pattern.
This is what I'm trying to say. So here you can take the first one.
Okay, so here, this could possibly be my best pattern, right? And I can't fill this in because of this contradiction. I can't fill this in because of this one. So like across three patterns, this one needs to exist in order to potentially make this the best solution.
Yeah. So
right? Like
if
I don't
you
want
go
to
into
take this
that
because
way,
this
yes.
because this is very small and this is some gigantic point value worth me not taking something here, whereas this is some gigantic point value worth me only taking this here.
Okay, yeah.
But if
it
you
makes sense.
disallow for this pattern, I can't take any score here. I can only do 0, 0, 0, 0, 0 when I could potentially just get some points here.
Take one of them, yes.
So negative or positive, you need all these OA patterns.
You have a very valid point, yes.
Yep.
Okay, thank you.
I will also say that I feel like I've gotten a lot of problems like this, a lot of questions like this. And honestly, if you write a solution that you think is not big O faster than a solution I presented, any additional optimizations you make is a potential for a mistake. And yeah, maybe we could have eliminated half of these patterns, but you don't have to, and you end up with an optimal solution anyways. But if you eliminated half of these and you end up with your TA going, what about this example? You're going to lose points. So, and this is the same thing with the problem that we did last week, which was finding the majority. You just want to get to a solution that works as optimal. The solution I wrote may not have done like all the things that, what about this, what about that? But like when you put yourself into that situation, you're more likely to, lose points than you are to gain any points that you can't gain, right? So if I write a solution that I think works, I generally just stop because I've tested it, I've considered it, it works, I'm going to move on to the next problem. Finding ways to shortcut anything in there is not going to help you. You're going to lose time and you could potentially make mistakes. So just, if you have all the time in the world, during practice and during writing homework, by all means, try to, find better and better solutions. But during the exam, try to avoid that. Bikash?
I have a couple of formatting questions. So one, I see the score as a function, but I think we could also have a score as a table, a helper table within recurrence function, where you have like basically n columns and j rows, and it will be of size on to fill.
Yep.
Is that format fine if we do it this way, that way, instead of the function for score?
You can fill a table if you want, or you can declare it as like, like if the question gives you a way to like explains what compatible means, explains how scoring is done, you can abstract that out into a helper function if you want to, or you can, calculate them if you want to. It's up to you.
And how do we, like, from a evaluation perspective, how do you know that that's a function, the first two are a function and not tables? And is it okay if we create the functions within the recurrence instead of subproblem?
You can do it in the recurrence if you want. And I think it's pretty readable the way I have it. I just say let's score I2. You can, if you feel you need to, you can say let this be a helper function and blah 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 blah. If that helps.
Okay.
Generally, the problems we give won't need a helper function, and if it does need a helper function, we generally define it for you. This is just me doing DPV problems that don't fit our class format as well.
Okay. Thanks.
Yep. Sharon?
Yes. In this walkthrough that you did, you placed the patterns above like the subproblem definition, and that helped illustrate the subproblem as like that you have these patterns available. But like in the exam itself, we probably want to like define what J is or what the patterns are directly in the subproblem definition when you're writing it out.
You wouldn't get a problem that's like this where you would have to like write out this particular, like you wouldn't have to write out the pattern. Like we wouldn't give you a question like this. It's like easy to make a mistake and it's kind of confusing. I wouldn't expect that. And if we did give it to you, you probably wouldn't have to draw out all the patterns unless we told you to. I was just doing it to illustrate what these patterns were.
Yeah, that makes a lot of sense. I'm just saying, like, maybe just saying the word pattern J, like, at least in my opinion, is like could be kind of confusing when you're trying to, so when someone else is reading this. At least that's my thought.
For pattern J, J is not defined to a pattern. J is just some pattern within this with this scoring function. It's an input variable.
Fair enough.
It's not a defined pattern. Is that what you meant? Or I'm sorry, I might not understood the question.
Yeah, well, you have to like explicitly state what is a pattern, and like if you didn't have the diagram, you wouldn't know what a pattern is.
Oh, it's defined in the problem. Determine the number of legal patterns. It's fun. Yeah, I don't have to redefine it. Yeah, I know what a pattern is because the problem statement told me what a pattern is. Let's see, yeah, the word pattern is defined. Even italicized for you. All right, I'm going to move on to the next problem. Yes, chat. My office hours are very long. Feel free to drop off if you need to go or need to rest. This will all be recorded, so I will go along as long as I need to cover everything. Would like to pick up the pace a little bit, but we are. It is what I do for my students. Right, table multiplication. So this is a I labeled it as windowing, but we'll get to why. So let us define a multiplication operation on three symbols A, B, and C according to the following table. Thus, AB equals B, BA equals C, and so on. Notice that the multiplication operation defined by a table is neither associative nor commutative. Find an efficient algorithm that defines a string of these symbols, say BBBBBAC, and decides whether or not it is possible to parenthesize the string in such a way that the value in the resulting expression is A. For example, on input BBBBAC, your algorithm should return yes because I'm not going to read all that. You can read it. So to me, I am taking a string. I'm not trying to fit it into anything, so not knapsack. I'm not trying to compare two strings. Sort of, maybe. You can kind of see like, oh, I'm trying to see what A and B is, but not really, right? We're not taking two long strings and comparing it. We're also not trying to like, try to maximize some previous subproblem along the way. What we're really looking for is we're looking at a string and we're trying to break it down into smaller pieces such that we optimize our score, or in this case, decide if we can get to a certain solution or not. So this is a very classic windowing type setup where you're given a string, you're not told where it's getting broken down, but you have to decide where to stick parentheses or breaks in order to figure out something. It's actually very much like the dictionary problem in a certain way. Like you're trying to find the way to break up the string into words, but it's like different. Now, so first we consider that this is a windowing problem. The second thing we should consider is it going to be all of n squared or all of n cubed, right? Because your windowing problem comes in two varieties. The way you should consider is that if I am to break up my my string at any given window, am I going to break up that string even further? And does changing it make a difference in my results? And so if I have a parentheses of some letters, I could potentially decide to break it here, or not at all. And so the decision of where those breakpoints are means that I have to try every single possible breakpoint in between. And if I have to try every single possible breakpoint in between, that's an additional O of n cost to calculate the optimal solution for just this substring, or this BBB. And doing so is I have a two-dimensional table that's O of n squared, and it takes O of n to calculate the optimal solution for each of those smaller windows. So it's O of n squared times O of n, which gives me O of n cubed. And so that is what my setup is going to be. Okay. And this is another one of those problems where we need to kind of define a special data structure. I don't like this problem in particular because we kind of try to avoid this in all problems, but we're still going to solve it. Okay, so let A be factors for the input. Okay, so this is similar to how CMM works. Like I'm not told what the input for this is. So I'm just going to define it. I'm just going to tell you, okay, well, I wasn't given a definition for this input, so I'm just going to make one up. So A is my factors, okay? T of ij here is a special type of tracking. I'm going to track all possible outcomes for substring A from I to j. Because there's no optimal solution here, right? I'm just saying what are the possible outcomes? What are the possible letters that I can turn this equation into? Because I need that so that I can then decide what I can take those outcomes to multiply with other outcomes to see what those outcomes are going to be. So I'm going to track some list of outcomes. It turns out this is not bad because I only have 3 possible outcomes of A, B, and C. So this is still a fixed size data structure of 3, size 3, right? So my recurrence then, and again, I like to start with my recurrence and then go to the base case. So for T of ij, I am going to add all the possible cross products of all the other cross products between I and k times k plus 1 and j for some k between I and j minus 1. And I'm going to do this across all my windows. What this means is that if I had some bunch of letters, okay, when I'm looking at A and A, I consider what my A times A is. Okay, that is one such thing that I possible product that I put in here. When I look at AAB, I'm going to look at what does A and AB give me, and what does A and B give me. Okay, so I'm going to add all the possible cross products of these two into AAB. Okay, now I no longer need to track what the parentheses for these two breakdowns are. I just have all possible solutions in there. So every time I want to consider this chunk of 3, I just have a list of possible solutions or possible products that I'm going to multiply across anything here, whether I want to compare it with just B, whether I want to compare with B and C, whether I want to compare with BCC. It doesn't matter. I have all the possible outcomes of this already. Doesn't matter. I don't need to look at all the parentheses again. I have all the possible outcomes. Similarly, BCC, I will have calculated all the possible outcomes here. And so same for for all other smaller windows. And as I do that, my possible outcomes gets tracked on the way up, and I don't have to keep calculating where to put the parentheses all over again. So in this case, when I have the solution, I would have known what B times B times B gives me in all configurations. I would have known what B times A gives me. I would have known what B times A times C gives me in all possible calculations, and then I just shipped the breakpoint between that window. Okay, and so this is how we write it. So we get all the cross products of T of ik and T of k plus 1j. So we take the breakpoint and we move it through our window and just add it all into our possible cross products. And now for T of ij, I have all possible cross products for this section, for this window. So set up all possible outcomes for that substring. And then I can use that as I get bigger and bigger. And so the number of subproblems I have here is 2 dimensions, all of n squared. And it takes this additional for loop right here, all of n, to calculate each of these subproblems, so all of n cubed. And then my final return is, does all the possible outputs or all the possible products between 1 and n contain the letter A? Because all I'm doing is I'm adding to a size 3 list every time. And if it contains A, then I have a solution. If it doesn't contain A, then I don't have a solution. And so this is all of 1 because this size right here is size 3. Okay? All right. I'm sure you have a lot of questions. Go ahead. Any questions on this problem? All right. Georgie?
Yeah, thank you. I don't know if you can answer this, but should we expect windowing problem for the exam?
Every problem that has been covered as either homework or practice in the lectures in the book is all fair game.
Okay. Thank you.
Yep. That's it. We've already told you, focus on your homework problems and your focus on your homework problems. They're assigned to you for a reason. Vikash?
Yeah. So when we say set of all possible outcomes, I'm guessing those outcomes are basically single letter, right? In the end, what are the possible single letter result?
Yep. And you only get 3, A, B, and C. Yeah. Like because if multiple combinations of this, let's say B times D is B, right? Okay. So for example, right here, for this one particular, if I do this, right? This B times B is B, and this multiplied by B equals B. Okay, so that's one possible outcome. The other thing I could do is potentially do this, right? And again, this becomes B and this becomes B. This also equals B. So it only has one possible outcome. I might calculate it more than once, but it only has one possible outcome. So this type of checking doesn't explode exponentially. It doesn't grow bigger because it's a fixed size possible outcome of 3 at all times.
Okay, so the cross product we are basically adding, which is for each Tij, we are adding a list of possible end values, and that list could be at max length 3.
Correct.
And if we are doing cross product of 2 lengths, it is at max 9. That is why it is not n to the power 4 runtime. It is n to the power 3 because we know that at max it is 9 multiplications. Okay.
Right. Yep. Yep. Karishma?
Hi, can you hear me?
Yes.
So this one, I know you have in here that it's at cross products of T of I to K, K plus 1 to J. And for CMM, when we were in lectures, we were told that for mathematical notation, that's going to be the minimum of C of I to K, K plus 1 to J, plus the cross products. Is how would we write it for in that way for this? Because on the exam, I think we're told that we need to put it in that minimum format.
It's only a minimum and a maximum if you're trying to minimize and maximize something. Here you're just trying to find out what the possible answers are. So I think cross products here is well understood and defined. I wouldn't try to put this into a minimum maximum because it doesn't make sense. It's very similar to your when you did the dictionary lookup problem. You're returning true and false. You're not returning minimal or maximal, right?
When you're saying add cross products, maybe I'm just confused on the verb of that. So are we adding it to the previous? Like maybe I'm just not understanding that.
So the cross product means I take all the elements of one set and all the elements of a second set, right? So if I A, B, C, and I have B, C, I'm just going to get the answer of multiplying them. Here, multiply is redefined for you, but I would get the product AB, AC, BB, BC, CB, CC. So I would cross product all of them, and then I'm going to add whatever those cross product is to the set. And my set, if I have repeats, I just remove them because it's a set.
Okay.
Yeah. Xiaoteng.
Jules, thanks for the office hour. Am I audible?
Yes.
Okay, thanks. I have a similar question on the recurrence definition here for the cross products. If this is a cross products, can you explain why are we using T index IK multiplying the T index K plus 1 and J? I'm sorry, I'm just not quite getting this part. If you can explain more about this.
So I mean, this is only possible and only allowed because this is what this is defined as a multiplication operation, right? It's saying let's define a multiplication operation to be this. And so in my notation, I said, okay, well, I'm going to multiply all the things from one set with all the things on the other set, which makes it a cross product. If this was like, let's define a summation operation of 3 syllables to be this, then instead here I would do a plus. It's just what the problem gave me. I didn't use multiply just because I felt like it. I used multiply because the problem said when you multiply these two things, it does this.
Okay, and why are we multiplying with K plus 1 and J? Can it not be? Yeah.
On any given window that you're considering, so suppose I have all the smaller windows calculated, right? So now my larger window is say B, B, C, C, okay? If all the smaller windows have been calculated, which is how windowing problem works, what I want to know is what are all the products that I can possibly have by dividing this as versus right? So I am just taking all the all the possible combinations I have on where I split this larger array, and I'm just multiplying it across every single, and then I'm just adding it to a set. And so my K here, right, is going between going between I, because this could potentially be in the middle of a full string, going between I and J, right? So this is where my breakpoint is, and I'm just trying every single possible K. And so the K is, if I equals 1 and K is equal to 1, then T of IK is T of 1, 1, which is here, and then K plus 1 would be 2 all the way to J. So this is 1, 2, 3. So this would be 2 to 4. So it's just where I'm breaking it up to because I know this is calculated. I know that this is calculated, this is calculated, this is calculated, this is calculated. So trying out everything to give me my cross product.
Mm-hmm. Okay. All right. Thanks.
Yep. All right. Yangjin?
Yeah, can you hear me?
Yes.
Yeah, I'm just wondering if our DP table can contain like multiple like characters, because I remember seeing a post where table can only contain like integer decimals and booleans, something like that. So I was just wondering if like
You can define your table to contain basically any data structure that you need, as long as it's well defined and you tell us what it is. I mean, I could also potentially, if it makes you feel better, you can do T of I, J, K. Equals true if what did I initially define this as? T of ij equals set of all possible outcomes for substring ij if I will get this right.
well, yeah, well, I'm just like curious because I know we can like convert it to like bitmask or something like that.
Yeah.
Just wondering.
This is allowed.
Okay.
Yep.
Got it. Thanks.
Lennon?
Hello, can you hear me?
Yes.
Okay, awesome. So would saying on an exam, would saying like cross products be rigorous enough? Because this looks more like a Cartesian product, just instead of pairing, you're multiplying and then removing duplicates. Is cross products rigorous enough, or should we be saying more mathematical terms like Cartesian product or something? Or is it as long as we define exactly what we mean, it'll be okay?
I think if you make it explicit and obvious, then you're fine. Cartesian product is probably a better. Yeah, let's do that. Sure. Let me change my notes to say Cartesian and.
Yeah, I guess I got a little confused at first because I saw cross product and I assumed like normal vector cross products, but this isn't.
Yeah, Cartesian products is the better word. That's fine. Yeah. Okay. Any other questions? Jafar?
Yeah. Thank you very much another time. So I did not got the Cartesian product, but I thought about something that you were just written. So T of I j k is equal to true if we have there exists L such that T of I L x equal to true and T of L plus 1 j y equal to true such that x times y equal to k. Is it something logical or no at all?
I again try not to grade student solutions in the middle of our hours because it really depends on how you write it, and I don't want to give you the false answer whether it's right or wrong without actually looking at it. And the best way to do that is to just write it in the.
It is inside. It is written. Someone wrote the solution inside but there's no TA who talked about it or respond to it.
Just hopefully other students can take a look at it, or maybe I'll try to take a look at it, but
Okay.
I don't want to
Thank
try
you.
to grade it. Yep. Okay. a couple more questions, and then I have to move on. Manjanath?
Joe, sorry if you already covered it. I got the point where you're doing the multiplication there between ik and k plus 1j. When you say Cartesian product, that's where I got stuck. Like, can you, sorry, can you explain that a little bit more?
I'm not, what do you, I don't know what you mean by explain a little bit more. It's this pattern that I'm trying to represent in here.
Sorry, I couldn't see your mouse pointer, but
right here, do you see this? Am I, yeah. Can I turn this into a, yeah, this right here? This is what I am trying to represent right here. Any given t of ij, which is some string of my my problem, I am going to try a k, which is right here, divided between the start and the end of my substring, and I'm just going to say what are all the products between multiplying these two plus all the products of my multiplying these two plus all the products of multiplying these two.
okay. I thought you're multiplying everything. Okay, gotcha.
Yep. Okay. Last one. I'm going to answer one more. Pardon?
Hey, thanks for this, but I was a very weird question. Like, I don't know if it makes sense or not. But for example, if I'm running through the table and I'm trying to fill, say, 1, 5, t of 1, 5, and I say k is equal to 2, then I go t of 1, 5 has to have the products of t of 1, 2, and t of 3, 5. Would I have t of 3, 5 at that point, or how would that work?
If you're using this recurrence, you should have access to every smaller window by the time you get here.
Okay, so it wouldn't be linear. It would go. Okay, got it.
Yeah, if you set up a recurrence correctly, you should have access to all the smaller windows up until this point.
Okay.
Any other questions? Okay, let's move on. So the next problem. So I am going to cover the palindrome sequence using reverse. Since we have so many windowing problems, we have yet another one after this. I think that this is just probably okay to skip the windowing explanation. Okay, palindrome subsequence. A subsequence is palindromic if the same, whether read left or right to left. For instance, this sequence has many palindromic subsequences, including A, C, G, C, A, and A, 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 A. On the other hand, the subsequence ACT is not palindromic. Devise an algorithm that takes a subsequence 1 to n and returns the length of the longest palindromic subsequence. Its runtime should be O of n squared. Again, you're not generally given the runtime of the problem. So looking at this, you can do this as a windowing problem because you're basically trying to find out what the largest palindrome in a given substring is, and then you're expanding on that as you open up the window more and more. And so, if I was to take, some, let's just pick right here. Oops. Oh no. Okay. If I was to take, hopefully you can read that. That window there, and then I add an A to it, I've expanded my palindrome, right? And then if I add a T to it, I've expanded my palindrome. And then if I add then another G or a C, I've expanded the palindrome. So you can grow your palindrome from the inside out. So that's how you would do the windowing. technique, go ahead and try to solve that. I am instead going to show you what the easier way to do this is. A palindrome is basically an LCS compared against itself. If you take the string and you reverse it and you compare it against itself, your longest common substring is your longest palindrome subsequence, right? Because it's just a string that repeats itself, right? So the way I solved this when I first looked at it was, okay, well, I'm just going to flip the string around and then do an LCS entirely. So I'm going to redefine my a second set of letters. So we are copying x of x into its reverse y and looking for an LCS. Let t of ij equals the length of the longest common subsequence in x of 1 dot 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 I and y 1 dot 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 j, such that y1 to n is the reverse of x1 to n. Okay, and then I have my recurrence definition. So I am first going to define what my y is set to. There's no reverse function in math, so you kind of have to just explain what that is. And so here I say my y of I is equal to this little equation here, which is n minus I plus y, which is the reverse. And I'm going from 1 to n here. And then where was I? Yeah. And then I am going to set, this is exactly LCS. Everything about the rest of the solution is LCS. This is an LCS base case setup. This is an LCS recurrent setup. And there's nothing special about this other than the fact that I have flipped a string backwards so that I can do this as an LCS problem. LCS problems are low-end square subproblems because you have 2 dimensions, one across each 1 to n, and then it takes O1 to calculate that subproblem. So they are total runtimes O(n) squared, and then you get the final return, which is O(n), and it takes O1 runtime. Yeah. Questions about this solution? Karishma?
Yeah, so in the subproblem definition of stating that y of n of x of n and the actual t of ij, but we were told never to use n of that. Is this okay that y is a reverse?
Sorry, never supposed to use n?
N, yeah, because it's be on a prefix. And putting n.
So my subproblem definition is very much defined as 1 dot dot I, y dot dot I, right? I am just further telling you that I am creating this other thing. You could leave this out. You could make this separate if you wanted to. Like, why is my yeah. And then you could use a separate line to define what y is. I mean, it's just like my subproblem is still defined between 1 and I and 1 and j. I'm just put in there what I'm doing, what y is set to, but you don't need to be there if that makes you feel uncomfortable.
Okay, and then one additional question. For this one, I know there's 2 solutions. I believe get to the same runtime, but on other questions, I think you talked about a solution for one of the other ones. Think of for that case scenario, is DP looking for the most optimal, if you end up getting to one of the solutions in a set of solutions that you guys?
We are always looking for the optimal solution. There may be multiple solutions that are optimal. There may be situations where the optimal solution is incredibly difficult, and we think that's beyond the scope of the exam. But we have a target runtime that we want students to hit.
So going back to the O of n squared one where you secondary array, and then it became O of n, you would be O of n in that case?
Depends on the problem. On that particular problem, we haven't graded it in a long time. But for that particular problem, I feel that like the TAs would discuss, and I would have suggested that we go with the O of n outcome. But it kind of depends. Like I said, it really depends. Like if we show you a O of n outcome on a very similar problem, and we say, hey, this is the optimal solution, then I think it's also fair for us to say on a very similar problem to also then be like, okay, yeah, we're expecting the open outcome. It just depends on the problem. There's no hard and fast rule. What you need to worry about is when you go into the solution, you just try to get your best, your optimal solution, and that's all you can really hope for.
Okay.
Yeah. Like worrying about that on like, oh yeah, can I give a suboptimal solution is not the approach I would go into the exam in terms of like how you want to attack it.
Okay, yeah, that was my underlying question. Okay.
Yeah. Okay. All right. Aaron?
Thanks, Joves. So, I don't know if this was answered, but you're doing a reverse of the original input. Would we have to mention the runtime for that too? Or like some small detail that's happening?
I think you can if you want to, but we've simplified the runtime question to the point where we're asking you very directly about each thing. So I would not. I mean, I would tell the TAs not to take points off for that because we didn't ask for it.
Got it. But if it is there, it wouldn't ding us.
No, we wouldn't take points for you giving us extra information unless that extra information is actually wrong.
Got it. Thank you.
Yep. Farah, last question, and then we'll move on.
Yes, hello. I just wanted to ask, because this part, like, it's not clear for me, the part of including I, like the AI element. Here, I'm not sure, are we including AI in both strings or are we not including them?
Yeah, no, you don't do it for LCS because on LCS, you are for longest common subsequences. For subsequences, you're allowed to skip a letter, and so we are not including the final letter. If this was a common substring where you are not allowed to skip letters, then you would state that you want to include the I and J characters.
Thank you so much.
Yep. All right, let us move on to the next problem. String cutting. I am not a fan of this problem because I'm not a fan of the way it's described. Again, it's one of those problems where like you spend 90% of the time trying to figure out what it's asking and then the rest just answering the question. So I'm not a fan of these type of questions. A certain string processing language offers a primitive operation which splits a string into two pieces. Since this operation involves copying the original string, it takes n units of time for a string of length n, regardless of the location of the cut. Suppose now that you want to break a string into many pieces. The order in which the breaks are made can affect the total running time. For example, if you want to cut a 20-character string at positions 3 and 10, then making the first cut at position 3 incurs a cost of 20 plus 17, which equals 37, while doing position 10 first has a better cost of 20 plus 10 equals 30. Give a dynamic programming algorithm that finds the optimal locations to cut this. Funny enough, the runtime to find where to cut has got to be longer than actually just doing a brute force cut, right? Like if we think about it, when we're looking at this, we decide it's windowing, right? Because it's a breakpoint. But if I was to tell you that cutting the string takes, O of n time to read the string, and I have k cuts, my runtime to do this as a brute force is O of kn. Worst case, I pay the cost of reading the entire string every time, and I'm going to make k cuts. K has to be less than equal to n. So at worst case, this is equal to O of n squared, which, bad, but we're about to show you a O of n cubed solution. So, it's a silly problem to me. But here we go. So the idea is that if I had a string like this, right, that is 20 characters long, regardless of where I make the cut, I have to read the full string as my input. So the initial cut, no matter how big the cut is, my initial cost is 20. Okay. Once my cost is 20, I have two possible outcomes. Either, I'm trying to cut 3 and 10. Either I have a piece of 3, because I already made one cut, and a piece of 17, and then I have to read this string of 17 in order to make the other cut of 10, right? So now I have this cost equals 17, because I can ignore this part. I'm just going to read this part. So now I have 3. The next one is position 10. So this is actually 7, and then this is 10. Okay. So those are my sizes. Okay, and then I'm done. Okay. The other possible way I do this is I start with 20. And instead of cutting at the 3, I cut at the 10. Okay. Now I read this left side right here with the cost of 10. And then I cut this to 3, 7, and I read this 10. Okay. So depending on where I do my cutting, I either get a total cost of 37 or a total cost of 30. So what I have? Yeah, 30. So this right here is considered optimal. This right here is considered suboptimal. All right. With that, do we understand what this problem is asking? Okay, good. Now, this is a CMM problem. We're deciding at a given window where the best places to cut is. Okay. Now we assume that the previous cuts have already been calculated of a smaller window. So across a single window, we're just deciding where the best place to cut is. And so that tells me that this is a O of M. To N or M? So we have, it's not O of N, it's O of M cubed. M is the number of cuts. What is M here? Sorry. Yeah, so it's all of M cubed. So using M. So yeah. All right, let us go with what the solution looks like and talk about it. All right, so much like CMM, we are going to define a secondary substructure because we need to know where the cuts are, not so much where we need to know the indices of where our cuts are, not so much where the cuts are. So we have to add 2 additional pieces to this. So we have let C of 0, 1, ... m plus 1 be the location of the m cuts. Note that C of 0 is equal to 0 and C of m plus 1 equals n, defined as the indices of the start and end of the string. Okay. Because I cut it in the middle, I need a different data structure to sort of represent where the start and end of each piece is, because that's actually what my calculation is dependent on. You could just do it directly with the cut, but it's a little bit more confusing. You have to say, like, if m equals 1, then my start is 0 and my end is m. But if m is not equal to 1, if it's equal to 2, then my start is at m minus 1, and it gets all sorts of confusing. So this is just a some simpler way to do this. Okay, so that I and j equal the minimal cost of breaking up x at cuts c of I dot 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 c of j. Okay, x being the substring. The minimal cost of breaking up. Why do I call this x? Couldn't I just call this a string? Didn't go as a placeholder. Right. Breaking up a substring at cuts c of I to c of j. Okay. So how is my recurrence set up? My recurrence is that I want to go between I and j for a k, such that I am minimizing the cost that that I had to pay to cut from I to k, from k to j, plus this is the cost of reading that substring, right? Remember, when you read a substring, you pay the entire cost of reading the substring. No matter where you cut, you have to pay the cost of this 10, right? And this 10 is calculated by where the end here is and the start here is. So this cost is c of j minus c of I. That's my cost for even reading the substring. Once I read the substring, I am going to calculate where I can cut it using k, such that I minimize the cost. I cannot minimize the cost of reading that substring, but I can minimize the cost of cutting that substring. Then I go from I to j to m plus 1, which is this right here, my c. Okay, I'm going until the very end of my string. And my recurrence definition is to say that if I am cutting from I to I plus 1, my cost is 0, because there is no cost or cut to make, right? If I'm reading from, if I'm reading from right, any substring of 1, I'm not going to do a cut, and therefore my cost to make that cut is 0, right? And then that's my base case. So if I get down all the way to some size where t of I and I plus 1, I cannot make a cut, and therefore the cost to make that cut is 0. I still have to read that substring to decide that I can't make a cut, and therefore that is still c of j minus c of I. So the cost to read the substring is 1, and then there's no cuts to be made, and so that the entire cost is just 1. Okay. All right. Questions about this problem and solution? Mitchell?
Hey, Joves. So usually when I approach a windowing problem like this, I kind of take the model from the lectures, and I start with my base case as being the diagonals, that first set. So like T of I. For purposes of this, is using that first off diagonal set sufficient, or would we also want to, just for completionist sake, say that T of I would also equal 0 for all 0 less than or equal to I less than or equal to n?
I think you can set it up either way. I mean, the only reason to do that is if you could potentially, if you set up your loop to potentially have k equal to I or k equal to j. So if like, so right here, my loop is k is between I and j because I don't want to try to cut a single, a one size array. But if I did do, I less than equal to k less than equal to j, my k can go up to j and it can start from I. Then I would do, yeah, t of I equals 0 is also fine. It just depends on, like I said, you write your recurrence, then you decide what your ranges want to be, and then you decide what your base case wants to be, and then you can adjust that however you want as long as it makes sense for you. The core of it is the recurrence. Everybody's recurrence should be about the same, and then your range and your base case is kind of depending on how you want to set it up. Imagine writing code, right? You can set your for loops in different ways depending on what your internals are doing, and it's all fine depending on how you want to do it.
Understood. Thank you so much, Joves.
Yep. Vikesh?
Yeah, so one thing that threw me up, I was working on this today morning, was it is not necessary that the input locations 1 to m would be in sorted order. And if that's not the case, let's say, it could say cut at like 10, 100, 30, 1, whatever. So we add something to sort.
The cut is not in sorted order?
Yeah.
That is true. It's not, doesn't say it's in sorted order. I would say that if we were to give this problem, we would either A, say that it was sorted, or B, allow you to say that you assume it's sorted, or if you want to give a sort algorithm, that's fine. I would be very upset if we penalize this problem because you assumed it was sorted, because I certainly assumed it was sorted. Problem doesn't really make sense if it's not sorted. So I would push hard to say we should have said that this was sorted.
So I'm still trying to understand why is ti to I plus 1 equal to 0 and not 2? Because that's the length of, I'm guessing, that minimum string, the base string that you're creating.
Why is this equal to 0 and not 2?
Yeah.
What is the cost of cutting a single length substring? Can you cut a single length substring?
So when when we say ti to I plus 1, I'm guessing that's the minimum length is 2, right? Oh, sorry, that could be 1. Okay, now I got it. Okay, so that,
yeah,
that could be basically 0 to 1, right?
Yeah. So yeah, I have it as 1. You could also set it as t of I is equal to 0, and then your recurrence would work a little bit differently. That's fine too. It's, there's different ways to set this up.
Okay, got it. Thanks.
All right. Amasoto?
Yeah, I had a question about when you said, can we cut a single length substring, right? So
Yeah.
to me, it's confusing because that would depends on how we interpret it. So we can cut it into like an empty string and the string itself, but then we could also say, no, we can't.
I don't think you could do that. I mean, I think if you set up your base cases and do all sorts of complicated like math and checks, you could. I didn't set it up that way. But I don't want to say like, you definitely can't set it up that way.
Okay.
Yeah, I wouldn't pay a cost to read a one. I mean, I pay the cost, right? I pay the cost to read the string here no matter what. And once I read the string, I'm going to decide I don't want to cut and I'm going to be done. I'm going to return.
Okay, thank you.
Yeah. Okay. Last question, Shanek.
Hello, am I audible?
Yes.
Hi. For the T of I to J, I was just wondering, is it referring to the substring formed by the cuts at I and J, or is it talking about the indices I and J of the substring? The bounds are confusing me. In the recurrence relation, I and J are going from 0 to m plus 1, but for the base case, we have 0 to n. I understood this as we don't really care what the length of the string is. We really care how many cuts there are. So
Okay. So yeah, you're right. I mean, I misspoke. So I and J is the location of where the cuts are. It is the location of where your cuts are going to be. I'm sorry. I misspoke. This is not saying a string of size 1. This is saying a string for which you are already at 0 cuts on that string is no cost to cut that string because you cannot make a cut. So if my T of if my C of I is equal to 5, my C of I plus 1 is equal to 20, right? This is a size 15 string. Because you cannot make a cut, because the cuts are already defined to be between 5 and 20, there's nothing to cut. And because there's nothing to cut, there is no cost to the cut. It doesn't matter what the size of the string is. I misspoke about that. I'm sorry. So T of I to I plus 1 is whatever whenever there's no cuts to be made, you're at 0 cost.
thank you. And then the bound should be up to m, or the bound should still be n in the base case, where the arrow is pointed.
They're still up to n because remember, in here definition, n plus 1 is equal to n, right? And therefore, my I is going up to n, and my I plus 1 is going to become the same as n plus 1. Wait, this will become
I mean, if you just have
that is that's m. Okay. Yeah, I think that's actually m. Let me go and fix my problem.
Sorry, and one last question.
No, don't be sorry. Correcting me is never something to be sorry for. Let me fix that on here, and then I will continue to m, and then okay, so that becomes n plus 1. J goes up to n plus 1, so that is calculated. J. Okay. Yes. All right. It should be m. Sorry. Continue.
Okay. One last thing. So in the dynamic programming guidance, it was mentioned that we shouldn't modify the inputs. Is reversing within like acceptable things that we can do? Because one reason like this didn't even occur to me was because we are changing anything in the input, right? Not for this problem, I mean for the palindrome subsequence problem. The one that you
I
covered
think,
before this.
yeah, I think it's allowed to declare. I mean, if you don't declare it as an input, you could just declare it as a table, right? Remember how I did that, kind of did that with McDonald's, and I declared a separate table to do all these things. Like, you're allowed to define a second table to track things, and you can define the second table to be the reverse of your input. And as long as you actually like show how you go and set that up, it's allowed.
Okay, and then if we define it as a table, then we can still have the indices start from values other than 1.
Yes.
Okay, all right. Thank you so much.
Yep. Okay, we'll move on to the next problem. Longest common subsequence. All right. This should be very familiar. I believe this is only different from what's being covered in the lectures because of N&M. I'm just gonna post an entire solution. I don't think this one should have too much discussion. Hopefully, so you're given two strings, x to xn, y to y1 to m, and you want to find the length of their longest common subsequence, that is the largest k, for which there are indices, and yeah, I don't like this math. Just looking for the longest common subsequence. And so my subproblem definition is T of ij equals length of longest common subsequence between x1 dot I, y dot, and this is just basically the palindrome one, except this is actually just the natural way to do this. So I go to n and m because the size of my two arrays are different. And so you set up your LCS equation. If they match, you add 1 to the previous best. If they don't match, you just carry forward whatever the previous best was and you keep going. And your number of subproblems is of n(m), not n squared, because the array sizes are different. So you have to multiply the two array sizes. And the runtime to fill the table, this is all 1 to fill the table. You have a two-dimensional array going from one dimension going from 1 to n, one dimension going from 1 to m, and therefore you have O and m. And then your final return is the very bottom right of your table, which is the final value, and then O1 to return that value. Okay. Any question about this problem? Sato, your hand is still up. I don't know if it's from previous question or if you have a new question. Oh, okay. Cool. All right. Now we move on to the final dynamic programming problem. This is 6.17 knapsack. I am going to again paste this entirely because we've already gone through 6.8, 6.9, 6.18, 6.19. So hopefully this is looking really familiar at this point, and it's basically just knapsack. So you're given unlimited supply. So this is an unlimited version, right? You're given unlimited supply of coins with denominations x1 to xn, and we wish to make change for value v. That is, we wish to find a set of coins that's total value is v. This might not be possible. Yeah. So this is a sum problem, which is very much just knapsack, where the weight and the value is set to the same thing for each coin, and your budget is set to be the value that you are trying to make change for. So let T of ij equals maxsum less than equal to j using a multi-set of coins from coins 1 to xi. Okay, so you're considering the first ith coins, and you want to make up to a maximum of j to see if you can make that change. Okay, so we go from, this is our base case, classic knapsack, and then our recurrence is, if our coin can fit into our current value that we are attempting to make change for, we either we take the max of either removing enough space to fit that coin in, which is j minus xi, and then adding the value of that coin x of I. And normally on a knapsack, this would be the weight, and this would be the value. But because the weight and the value for a coin is the same in this case, they're both going to be x of I. And so we are going to take this value and try to maximize it. And we're going to compare either taking out the a coin to fit this coin in is better than leaving it alone. If I just didn't consider this coin, was it better off that way? And if I can't fit this coin into my value, then I'm just going to take whatever the previous best was, because it's as if this value wasn't considered at all. I go through my for loop, and this is O of n times v, because that's the number of subproblems I have. It is two-dimensional. One is across 1 to n, the other is across 1 to v. It's O of n v subproblems. And the runtime to do this is an O of 1 runtime, so it's O of n times v. And the final return is whether the maximum value for all coins considered at the value that you're trying to fill is equal to the actual value you're trying to make change for. Because if you can make 50 cents with all your coins, when you're considering 50 cents, that means you can make change for 50 cents and so forth. So this is an O of 1 time to extract. Okay. If you have questions about this, go ahead and ask it. But if you tell me, oh, we can do this in one dimension, that is true, and I will show that next. So any question besides that, you can ask. Nishink?
Yeah, so this is about the base cases. So in this one and then in the previous one, it seemed like we were defining the top left corner of the DP table twice, like specifically the 0, 0. So like I think in some of the solutions they put like 1 is less than or equal to j, which is less than or equal to v. So is it preferred to do that so we're not defining the 0, 0 twice?
It's up to you. If you want to do it from 1 because you recognize that you don't want to accidentally have a contradiction in your base case, by all means do it. I like to do my base cases in what I think just how I would like naturally explain it and define it, and so I don't bother doing that if I know that I'm not going to have a contradiction. Whatever you feel comfortable with, as long as it works, it's fine.
Okay, yeah, just wanted to make sure we wouldn't lose points for the redundant definition.
Nope.
Okay, thank you.
Aaron?
Thanks, Joves. So in the final return, you're doing a comparison, which reads to me as like a Boolean, so true or false. And I solved this problem using a Boolean table of T's and F's, or zeros and ones, and that's fine, right?
Yep, absolutely.
Okay. Cool. Thank you.
Okay. All right. So as promised, I will present to you 6.17 simplified. Before you ask, there is no preference to either of these solutions. Pick the one that you're most comfortable with and that you are most likely to write correctly. So because we have unlimited uses of all the coins, we don't actually have to track that. So what we can say is let T of j be the maximum sum less than or equal to j using a multi-set of coins from 1 all the way to n. Notice here how I say x of n, because we are encoding within T of j all the coins that are considered. I don't have to track it. So if you right here say x of I, you're going to lose points for it because x of I here is undefined. There is no I here to define what x of I is. I'm just saying I can use all coins. You also don't need this. You can just say all coins, right? You don't actually need to call out what the boundaries of the coins are. Does not really need it. Okay.
Excuse me, Joves. It looks like you stopped sharing your screen. I don't know if you know that or not. Maybe it's just me. I don't know. I don't see your screen anymore.
Can anybody else see my screen?
I still see it.
Oh, you do? I'm sorry. Then my bad. Sorry, I can't see it. It's me.
Okay.
My bad.
Try refreshing. Sorry. Okay. So here our solution then is all we're going to say is, okay, well, if we remove this current I, can I fit? Okay, so if my current I is less than or equal to j, and I'm going to remove it and see if I can get a better value by taking this max. That's what this is. Now, there could be a possibility that my every coin cannot fit the value that I'm trying to make change for. So I need this otherwise here outside of this max to say, well, if I can't find any coins that can fit into the value I'm trying to make change for, then just return 0. The best value I can make on a given for a given value with no coins is 0, right? So that is your 0 otherwise. And then I am going to go from 1 to v for my j. Now, notice how the runtime here, O and v, is the same. You're not getting anything by doing this solution versus the other. Your overall runtime is the same. Your size of your number of subproblems, however, does change. It's O of v. I'm only tracking one single dimension here, which is j. J goes from 1 to v, so my number of subproblems is O of v. But I do this 1 through n loop on each of these table entries, and therefore it's all of nv. And so my final return is t of v equals v, same thing up here, and it takes all 1 to extract. Okay. Any questions about the simplified solution?
Yeah, I guess I'll go ahead. So I guess if I'm understanding correctly, so we're allowed to not consider a subset of the problem for the subproblem definition because we want to consider all of the coin denominations?
Correct.
Okay, thank you.
All right, cool. So with that, we are done with dynamic programming. We will now move on to DNC. DNC should go a lot faster. It is a little bit, these problems are not super complicated. Some of these aren't actually like, so these other problems, some of this one, this one, this one, and this one, and I think this one are thought problems that I will go over quickly, and then the rest are sort of like a written algorithm problem. Okay. We are going to take a break, 2 to 3 minutes. Go get yourself some refreshments, and I will be back. All right. How's everybody doing? Let's get back to it. Student asked if we can do another session. Yeah, these are the ones I'm going to go over. I think this will probably take hopefully less than an hour. I can do a second session if that's what everybody prefers. I just don't know of a good way to take a poll. Let me see. Let me see my calendar and see. If I do another session, it would either have to be. It'd have to be on Tuesday. It would be after dinner, so it'd be pretty late. Okay.
Yeah, I would say let's just continue today so then people can review the rest of the day and tomorrow.
Yeah, I think that's best. I just it would be really late, and I think it would be like even more miserable. So I'm just gonna try to go through this quickly. Most of these aren't that bad. These are just kind of like discussions. So hopefully we can get through them. All right. 2.4. All right. So 2.4 is really just giving you different ways of trying to calculate the runtimes of a bunch of scenarios. So this is just a sort of a way of asking what is runtime. So let's go over each of them, and then we can talk about the runtime. So algorithm A solves problems by dividing them into 5 subproblems of half the size, recursively solving each subproblem, and then combining the solution in linear time. So we use the master theorem. A equals 5. That tells us how many subproblems that we are going to try to solve at each recurrence, at each subsequent recurrence. We divide the subproblem in half the size, so b equals 2, and then it takes linear time to solve the problem. So it's d equals to 1. Careful that d is not the runtime. D is the exponent to this part right here, and 1 means a polynomial power of 1, which is O of n. So this is our equation: 5 times t n over 2 plus O of n. We figure out what log of b, log of a over with the log 2 of 5, which is log b of a, is equal to 2.33, and so 1 is less than that because that's what d is. And so what we're looking at is O of n to the power of log b of a, which is n to the 2.33. So that's your master theorem at play here. Part B is solves problems of size n by recursively solving 2 subproblems of size n minus 1, and then combining the solutions in constant time. So we are going to be using Christian's method, which is just to kind of talk through it. You could do this with substitution if you prefer. I just think it's easier to just kind of figure it out. So we have 2 times. So we have 2 subproblems. Each subproblem gets smaller by t of n minus 1. And it is a constant time to combine this. So this is plus c. Okay. So because each recurrence doubles the work, says a equals 2, and then you have n recurrences, it's actually all 2 to the n proliferation, and it dominates whatever work this is. It's like nothing compared to the 2 to the power of n work that you're doing. So you end up with 2 to the n. This is not a good runtime. This is considered NP hard. If we were to if this is actually like the best runtime you can get, this is NPR. But that's not where we're at, right? We're just asking TS3 algorithms, which one would you choose? Which means that even though this is a NP, an exponential runtime, there are better solutions. Okay. Option C says size n by dividing them into 9 subproblems of size n over 3, recursively solving each subproblem and then combining the solution of n squared time. And so 9 is the number of subproblems we have. B equals 3 because we're dividing it as up into by 3. And D is 2 because we're doing all of n squared runtime. So this is our equation: 9 times t n over 3 plus n O of n squared. We solve for that using our trusty master theorem, which gives us this equation here because log 3 of 9 is equal to 2, and d is also equal to 2. So you take n to the d times log 3 of 9, which is sorry, log b of n. Yeah. So you end up with this this equation. So O of n squared times log 3 of n. So this is really bad. So that's definitely not the answer. Log n squared. So log 3 of n is smaller. Is it smaller? I think so. I actually can't tell if it's a or yeah, because the 0.33 is bigger in the exponential scale, where this is like some log scale that you're just going to multiply this for. So this is going to be a smaller number than this number. So C is the best. Okay. Any questions about this? Student asked, why is it log 3n in C and not log n? This actually simplifies to log n. You could just simplify to log n. That's fine. Yep. Okay. Nishank?
Yeah. So if we were to do part B using master theorem, would A be 2 and then B be n minus 1? And then
you can't do this with master theorem because the n minus 1 is not something you can represent with the master theorem into this equation. You actually have to do this as substitution if you wanted to do it in a different way. You could also just reason it out, which is what I say Christian's method is. You just kind of know that this left side, this part right here, the recurrences absolutely dominates this, and because of that, you can just get your runtime based on this. But you can do the substitution method if you want. I don't think you can use the master theorem on this directly.
Okay, thank you.
Yep. Okay, good, great. Next problem is 2.12. All right. 2.12 asks how many lines as a function of n in O of n form does the following program output? Write a recurrence and solve it. You may assume n is a power of 2. So we have a function that says that if n is greater than 1, so we have a base case, print line still going. And then it calls the same function, the recurrence, the recursion of the same function of n over 2. Okay, so then you print one line and then call the function on half of the input. Okay, so what does it come out to? Well, it comes out to this to this equation. We have n over 2, which is how often we how big the sub problem gets reduced by, right? N over 2. That's right here. And then we call the function twice. So we have 2 times t of n over 2. And this one line right here that prints still going is an O of 1 operation. Okay. So with that all in mind, we solve for this. So a equals 2, b equals 2, d equals 0, because d is the exponent of this work value, and n to the 0 is equal to 1. So therefore, this is a 0. Okay, so then we solve for this. Log 2 of 2 equal to 1, 0 is less than 1, and therefore our runtime is O of n to the d, and d is 1, so it's O of n. So this takes O of n time to do. Okay. Any questions about this? Cool. 2.15. Just speed running this. Love it. All right. Don't worry too much about 2.15. I'm going to go over it, but this is just something you can do if you want. But this kind of thing is unlikely to be on the exam. So 2.15 is saying in our median finding algorithm, section 2.14, a basic primitive is the split operation, which takes the input on array S and a value V, then divides S into 3 sets: the elements less than V, the elements equal to V, and the elements greater than V. Show how to implement the split operation in place, that is, without allocating new memory. We normally don't ask you to write pseudocode like this, but since this is actually asking for implementation, pseudocode works best for it. And so we are going to write this this function using in-place replacement. So we don't want to allocate new memory. So we're just basically going to start a lot of swapping. This is actually, if you've ever taken a very intro to C class, one of the first things you do is write a swap program in C. At least at Georgia Tech you do. I know at Georgia Tech when I took my first C class, it was like, this is how you write swap in C. So this is basically it. Okay. So what we're going to do is we're going to go from beginning to end. We're going to keep track of a pointer. And we're going to say, okay, if some value at I, right, as I'm going through my array, is less than V, V is my pivot, my target pivot, okay? I am going to put it at where T is, which is my first value, and I am going to swap them. Okay, so this is the swap code, right? You create some temp equals st, which is where my pointer is, and then t replaces where my I is, which is the value I care about, and then I gets replaced by temp. So you just swap them. Now I move my pointer up 1. So what I'm doing is, as I'm taking this array, okay, I go, my t is right here. As I compare values, anytime I have something that is less than V, I wanted to put it on the left side of my value. So I go, okay, well, I'm going to put this here, and I'm going to put this here. Let me use a different pointer for that. And now this value, no matter what happens next, I know this value is correct. This value is done. So now I move my pointer down to the next value. So as I go, every time I need to swap, I swap into a new pointed area, knowing that this value is going to be less than V, right? So what's going to happen though is that what happens if I take a value here that was already less than V and I swap it? Well, it's okay because I'll get to it eventually. As long as I keep swapping, what might happen is that this value right here is less than V and it gets swapped here. But when I get to it, I'll swap it back here. So it works out. It works out that I keep going forward and I swap everything back before V. So now at some T, right, because T is going to stop incrementing at some point because every value afterwards is going to be greater than V, or greater or equal to V. So T is now at a spot where everything to the left is less than V and everything to the right is either greater or equal to V. Okay. Now, I then continue from T, my second for loop from T to N. So I've ended up where I am. And I do the same thing. Everything that is equal to V, I swap into this next section of my array using the same swap implementation, and I keep tracking. So everything gets less than V gets swapped into the beginning, everything equal to V gets swapped into the middle, and everything that's left are things that are greater than V and I don't touch, and they are all partitioned correctly. This is a O of n time to sort, to partition, and it does it all in place. Okay, so correctness here is the first for loop will take all values less than V and move them to the front of the array, swapping out values and incrementing T as more and more values less than V are added to the front of the array. The second for loop will take all values equal to V and do the same thing, and move them to where T has ended, which is after the values less than V. So all values equal to V are now before the values greater than V. Going from 1 to n is O of n. Going from T to n is also O of n, because our pointer keeps updating, and this takes O of n time. Okay. Any questions on this particular implementation? You won't be asked to do something like this on the test, but kind of interesting to do. Questions? No? Great. Next problem. 2.17. All right. I am going to give you two solutions to 2.17. I have one that you should feel comfortable writing and understand, and I have one that's more concise and a little bit trickier to not trickier to write. It is a little bit more, you have to be more confident in yourself in order to write a solution like this, because, you know, come exam time, I recommend following something more to like this, because you give yourself more space to explain your answer, and you know, it's a little bit less daunting to write this way. So you're given a sorted array of distinct integers a1 dot 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 n. You want to find out whether there is an index I for which a of I equals I. Give a divide and conquer algorithm that runs in O of log n. Now, always be wary of, oops. Be wary of extra information given to you. If you're told the numbers are distinct, it probably matters. Okay, it probably isn't just thrown in there for the sake of, you know, adding information. So it being distinct actually ends up mattering. And if you're giving a problem that has, like, you know, here are the set of numbers, and here are, you know, they're special in some way, you probably need to address it in your correctness. Okay, so the solution here is that we are going to modify binary search to use a updated dynamic target. I believe we did something very similar like this last week when we did the first missing natural number. So this is actually a very, you know, kind of a similar approach. So we're going to perform a modified binary search so that on x equals n over 2 to start. So x is our target. This is the target we are looking for. And modify the decision to continue searching left or right as thus. If a of x is equal to x, okay, then that is what we have found. So then return x and we are done. If a of x is greater than x, then search on the left with x equals the middle index of the left half of our array. If a of x is less than x, then search on the right with x now set to the middle of our index on the right. Mid index is calculated relative to the subarray. And then if so like, you know, you don't just say, oh, you know, my subarray is 10, therefore my mid is 5. You don't want to do that. You want to calculate relative to where the midpoint of their subarray is. So if the subarray is between, you know, 50 and 100, your x is actually set to 75. It's not set to 25. Okay, so you need to be careful of that. If the binary search ends without finding an instance of x equals x as defined above, then return not found. Okay. Yeah. So if it's found, return it. If not, if at the end of the binary search ends, you haven't found it, return not found. Correctness. The array is sorted, so binary search allows us to find a value x. Okay. So this is what the student asked about earlier. You know, can I write this line? You absolutely need to write this line. I can do a binary search because my array is sorted, but that's not enough to give your correctness. Why? What else are you doing with binary search? This is just a starting point to say this is a black box I chose, and I can choose it because my array is sorted. Now we have three cases at each recurrence. If a of x equals x, then we have found the goal and we are done. Okay. If a of x is greater than x, then for all subsequent indices I, a of I greater than I, we need to search to the left of this midpoint, which x is set to the mid of the index of left. So basically, if my a of x is greater than x, right, then everything to the right of that is also greater than the index, because I've already shifted. I've already gone too far on my values to match my index. So everything has to maintain that shift to the right. Okay. Why is that? We'll get to that. If I of x is less than x, and for all previous indices of I, A of I is also less than I. We need to search to the right of the midpoint with x set to the mid index of right. This property holds because the array is sorted and holds distinct integers. The distinct integers here is important. If the integers are not distinct, we run the risk of crossing over our target during the search, right? We only know that everything A of I is greater than I after our A of x is greater than x because we can't repeat numbers. And if we can't repeat numbers, our shifted search space is always going to be shifted on the right side. Similarly, if A of x is less than x, all previous indices is also less than its index because we cannot repeat numbers, and therefore that shift is maintained. It can only grow larger, but it can never be, overtaken because we're not allowed to repeat numbers. So the distinctiveness of the numbers here matters. Thus, we can eliminate half the array at each comparison step. Our runtime is that we made a modification to binary search, and it's to calculate a new target for each occurrence. The step takes all one, so the overall runtime remains that of binary search, which is all login. Any questions about this particular solution, Jafar?
Yep, thank you very much. So if we don't have distinct integers, is there a way to do it in log of n?
If you don't have distinct integers?
Yeah. Of course, we can do it to O of n, because if we want to go over the array, probably this O of n.
I don't believe, I can't think of a way to do it in binary search, because the key to binary search and all binary search variations is that at any given point that you do a check on the target, you have enough information to go left and right. It is a very key property that allows binary search to work. If, however, I hit all AFI and my value is not set to it and it's less than right, I can't be sure whether there's a repeating number on the left such that it could exist, or I need to go to the right, right? Like one possibility is to go to the right, but the left side could also have repeating values that overlap and could possibly cause it to happen. So I don't think you can do this in log n if the numbers are not distinct. I think that's actually a requirement for this to kind of work.
Thank you.
Yep. Okay. Now, I'm going to give you a simplified solution that you can, that's just going to demonstrate how we grade and what we consider in this class. But it is not something that you have to do, nor is it something I even suggest you do. So you can give a very concise solution such that we modify binary search to always look for at each step A of mid equals mid. So the target changes with each recursive call, and that's it. That's all you really need. The reason why this solution works is that once we have established what the target is, if the target is found, return X and we are done. That's naturally what binary search does. This right here is actually not a modification, right? If A of X is greater than X, then we search left, okay? Which again is not really a modification. That's what binary search naturally does. If A of X is less than X, then we search right. Again, not a modification. It's actually what binary search does. Mid index is calculated, okay? And then we say if it's not found at the end of binary search, return not found. Again, that's what binary search naturally does. So the only part you actually need to modify is that every time you look for a target, you modify what that target is. Is A of mid equal to mid? And that's the only thing. Everything else is handled by binary search. If you have a deep understanding of what binary search does, or any of the other black boxes you are trying to work with does, you can make as little modifications as needed to get it to still work. Now, are you going to be comfortable giving a 3-line answer to a question on an exam? Probably not. And if you do, and you're nervous about it, I would suggest that that's correct. I probably wouldn't give this solution on an exam. I probably wouldn't give this solution on a homework. I know as a TA that this solution works because I have seen this kind of thing over and over again. But as a student, I probably wouldn't have done this. But it is to say that when we go and grade your solution, we only care about whether your modifications work or not. If the modification works, everything else can be left up to what binary search already does, and you are okay with that. So what that means is that if you get a solution somewhere between this and this, like if you leave out this part, that's fine. If you leave out this part, that's fine. If you have this and this and leave out this part, that's fine. Some area in between these two solutions is also correct. Okay.
Joves, I couldn't see what you were pointing to
correct.
when you were saying this and this.
Okay. Sorry. If you left out this part, this is still a working solution. If you left out this part, this is still a working solution. If you kept those two parts and left out this part, it is still a working solution. What I'm saying is that this is a very detailed solution. Okay. This is a very simplified solution. You may not be comfortable writing this, which is perfectly understandable. You may think that this is too much, which is also perfectly understandable. Anything in between, as long as it hits all the right requirements, is a valid solution. And this is what we see as TAs. We see something super, super long. We see something super, super short. As long as your modifications work with the rest of the black box algorithm, it's okay. Okay. Karishma?
Hi. So for this, consider the zero-based. So when I was comparing this, the I as the midpoint, I would +1. Because if we're saying that index have value